So like you have different strategies. How do you pick between each one of them dynamically across different market environments?
Super cool. All right. So we've got similar projects actually. Well, similar. We've got few projects where we are using AI. One of them is automatic pricing. We do try to automate pricing with reinforcement learning. Actually, we've got agents deployed in production, which are, tweaking a bit the prices of the queries inside of the graph. So this is the space, more or less, right? Automated decision making. Right.
I'm interested in both. I haven't ever shipped anything in AI, so I'm hoping that the lab I can actually get something and then put it on GitHub. My background is product management.
Got it.
So I think I just need to have enough to be able to go in and
So you want to put ML in production?
Yeah, I wanted to be able to do something small, and then I probably wouldn't be able to do that as a full engineer. But I think both sides are growing, and so being a product manager who actually ship something or understand the content more deeply than others will allow me to kind of enter those spaces.
So that's the talk, right? Everyone right now is using ChatGPT probably. Yeah. I'm like, who's using? I'm using, sure. Right? Yeah. But the goal of this talk is to show you something that there is something deeper down there, and those are decades of research, right? And now we see that prompt, but below that there's a lot of stuff, right? And I will be sure. Yeah. So I think okay.
There's a specific also use case. I've been putting a proposal for the graph itself, which hosts this.
Yeah, I know.
And some of the customers are trying to figure out how do they optimize their index or allocation. And there was a really great article that traced me back to Semiotic about how they were going to do allocation optimization.
Yeah.
That seemed like being able to understand the concepts.
Cool.
Would help me to explain.
Anu won't be here. He's the guy that is working.
I would love to.
Yeah, so we are dropping new blog post on this because there's new version of index or allocation optimizer that was just put in production like a week ago or two. Yeah. Okay. So you can shoot us if you want more. So there'll be new blog post, like I'm saying, like incoming. Yeah. I was supposed to review that this week, but guess what? I was quite busy with preparing this tutorial. Sweet.
I'd love to.
All right. He's cool guy. He's very responsive. So just shoot direct email to Anya. I think that would be the best. All right. So.
Sure, Tom. I'm on the AI side. I'm a product designer. I'm just things are moving faster than I can keep track of right now. So I'm just here to drop in and see what you all are up to.
Yeah, awesome. Yeah. So you're more from blockchain side or from AI side?
AI side.
Got it. Okay. So I'm from AI side. I've joined blockchain and I was thinking, oh my God, blockchain is so fast. And then after a year in blockchain, it's like, I'm looking back in AI like, it's not one chain. It's like, right? It's like, and I've got a few slides on this as well, right? Because right now, I think that it's just we need to start filtering what is important or not, because it's just too much. I'm overwhelmed. I've got slides on this. Awesome. So I'm addressing this partially. I'm addressing this. I'm doing this because I want to feel what's your. We'll give like 5 more minutes maybe, or should we just start? You tell me.
Up to you.
What do you guys think? Should we start?
Yeah.
All right. So, welcome everyone. A pleasure. I already meet some of you. So I'm Tom. I'm VP of Engineering and Head of AI at Semiotic Labs. I joined Semiotic Labs a year plus ago. But before that, we are long collaborators. There's one co-founder of Semiotic Labs, Ahmed, the CEO. Another co-founder was supposed to be here, but he's not for now. And we worked together back in days in IBM research on AI, on some of the things that actually I'll be showing you here. And I was wondering, should I put some slides on? Yeah, and I was like, okay, let's not be so self-centric. All right, so happy Cinco de Mayo, everyone. Today is, yesterday was May the 4th. Today is Cinco de Mayo. This is awesome. Of course, I generated it using Gen AI, right? By thinking how to start this talk. And here's more or less the agenda, right? So I'll just briefly tell you something about Semiotic Labs, what we are doing, why we are here. We are part of that ecosystem. It's not let's say, mistake that I'm here. It's not like an error in the system. we've been with the graph for a while now, for 2 years almost. Then evolution of multimodal AI. I wanted this talk to be really big and give you some kind of foundational thing. I wanted to talk about evolution of architectures. And then I was like, yeah, it might be A, too deep, and B, I think I'll need 2 days to talk only about this. So yeah, but I hope that you will learn something from it. Then lunch break, and after the break, there will be 2 hands-on tutorials. I changed the first one for a reason. So I wanted everyone to learn what is MNIST. And then I said, okay, MNIST, like by looking at what AI can do now, just seems a little bit ridiculous, but you should know, because everyone in machine learning space just, MNIST, all right, not rings a bell, right? So that's why I was thinking about MNIST first and digit classification. I'll show you some image classification on CFAR, then coffee break, and we'll do second hands-on tutorial. And then we'll end up with some closing remarks. All right, so a few words about Semiotic. So the company was founded in 2020 by cryptography and AI researchers. Our focus was on applied research and innovative Web3 products. We got funding from National Science Foundation, from Headline, previously Infinity Ventures, and from Lines Capital, and of course by the Graph Foundation. We joined the ecosystem as you're seeing in here. We got first partnership. We've got Wave 1 grant and Wave 2 grant, and then we became the core developer around in December 2021, I think, right? Yeah. Also, we are developer of the ODOS, the optimal liquidity aggregator. So our areas of expertise, as I said, artificial intelligence, cryptography, intersection of those two, and of course, software engineering is at the back, right, fueling those two. Right, so some of the projects, as you just mentioned, right, indexer allocation optimizer is one of the things that we developed and it's put in production. So every indexer who is allocating can use that to support. It's a decision-making system, but of course we allow the indexers to have some kind of a control on it. Another thing that is actually in production, I was mentioning that the reinforcement learning solution. So AutoAgora, Alexis is the core developer. He was the author of the, let's say, yeah, he led the development and research for more than a year. Also in production, indexers are using that to let's say get better revenue. New project that is ongoing is of course natural language interface to the graph. I guess no surprise in here. Also, we are using LLMs. If you heard what LLMs are, right there. From the cryptography side, Gokai just joined, another co-founder, so he's leading that part. So we are working on a few projects, verifiable payments. We are just finishing actually. We are finishing working on the first prototype, and we plan to integrate that with the protocol within the next month probably. The goal is that we are making the payment systems inside of the graph more robust, more secure. We did plenty of work in the area of snark research, not AI totally. I won't even go deeper. If you got questions, Gokai is there. He'll gladly answer what is happening down there in the snark world. And then verifiable indexing. This is a new initiative that we are starting. We've been discussing that actually for a year now. So let's say we respect that problem.
So that last one, supplement or replace current POI?
Replace, probably, right? But it's ongoing. We are spinning that up, and we are going slowly. If you know POIs, then, well, you understand some pieces. So you understand that there is, right now we've got, do you know GIP 42 about world of data? So there are different formats of data and different data pipelines. So we're looking at right now at Firehose in particular. That's streaming fast. Another core developer is looking, and we are, it will be a long process, right? Because of the variety of the things and complexity of the problem. All right. So also we are, as I said, developer of optimal liquidity aggregator. What can I say? ODOS is cool. If you're swapping data, use it. Instead, if you're swapping from A to B, ODOS will find a route for you. You don't have to use, use this DEX or that DEX. It's a DEX aggregator, so it's going through all the DEXs. It's also looking at the liquidity pool, so actually you get a better ratio, right? And it's multi-input, multi-output, so you can clear your crypto dust, and it's magic. I don't know. I'm not part of this, but it's super cool. So if you like blockchain, then it's working on those chains. if you're swapping coins. All right, so now the core of this talk. And let me start from the following. So I already started with Cinco de Mayo, right? And what you can generate with AI. So now, okay, yesterday it was May the 4th, right? So of course I played and like, okay, imagine Darth Vader visiting, like visiting San Francisco, right? Visiting Presidio, and like, and the verse, okay, this is super cool picture. Then, okay, what if there are stormtroopers? Okay, what is he surrounded by? What is if he's actually celebrating Cinco de Mayo? Damn, it looks awesome, right? And then I said to ChatGPT, okay, may the 4th be with you. I was like, and that really blown my mind. Oh, I see what you've done there. So with, as I mentioned already, with Ahmed and Alexis, with IBM research for a few years, I remember a talk from like, I don't know, 7-8 years ago, when one of the speakers, invited speakers, was like, oh, actually, AI understanding jokes is a hard one. Well, I think we are here, right? I see what you did down there, literally blown my mind. It's like, okay, so what just happened? So let's go through the news. What just happened, right? So probably every one of you who heard about OpenAI. All right, who heard about ChatGPT? Everyone, right? I guess. So probably setting world records, right? It's mind-blowing, right? The adaptation. And of course, it's tricky. Even in here, like 1 million backers versus 1 million nice books. First, the comparison is not fair already because the criterion 1 million off is not 1-to-1. Moreover, ChatGPT, they already got people using API, right? For GPT-2, GPT-3. So, they already got a huge user base. Still, it's mind-blowing, right? And then, of course, I asked ChatGPT what it's thinking about it. And there's a nice paragraph that I actually agree. It's a significant accomplishment and clear indicator that my service is providing value to large user base. Of course, from the hypothetical point of view of a product developer, right? So amazing. So, okay, what else is in the news, right? So, okay, AI coming party, right? Okay, Stable Diffusion, which is yet another success, right? 1 billion evaluation some time ago for our open source product. It's quite amazing, right? Truly open source in a sense. Midjourney arrives, and then Microsoft Bing right now uses OpenAI's DALL-E to turn text into images. Damn, all right. Microsoft, right, where are you on that? Okay, so you've probably heard Microsoft, founded, like, made a deal and they invested 1 billion in OpenAI. That was mind-blowing. It was 2019. Well, we've got 2020, 23, 4 years later, 10 billions, and the deal is huge. There were many things happening in the meantime. Microsoft was slowly pulling it, like, hey, we'll give you more computational power on Azure. Hey, we'll build you supercomputer. Hey, take our 10 billion. It's awesome, right? And it's mutual. Think about from the point of view of OpenAI, your core product, the thing that you're working on, the thing you're researching right now is going to be streamed all over the planet, inside of Microsoft products. It's mind-blowing. It's win-win situation. I really love that. And of course, chatbot is becoming the thing in the office. And I start to wonder, like, is it all because they want to really bring Clippy back? Can you imagine? Who remembers Clippy from like, yeah, right? So check this out. It's an old news, right? Like 2 years. It's 2 decades, right, in this space. But actually, I can imagine Clippy being fueled by GPT-4 or whatever, right? Yeah, kind of like a joke, but maybe there is something in it. All right, so how are the other ones? Like IBM. IBM, this is awesome. April 20. Okay, today a workforce should prepare to work hands in hands with AI. Cool. Not even 2 weeks later. Well, actually, we think that AI is going to be such good that we are stopping hiring. So if you read carefully, 30% out of 26,000 workers are going to lose their job, or that would mean roughly 7,800 jobs lost. That's rough, IBM. I don't think that's well played, by the way. But well, IBM. So what others are doing? Okay, so some companies are banning like Samsung, right, because of the proprietary. They're afraid that they will leak some proprietary data, their employees. Italy banning, yes. Yeah. Cool. Yeah. Good comment. It was kind of like a joke, as ex-IBMer, I feel that I can make a few jokes. But we were in IBM research, actually, the 3 of us. There's Sam and there's Alexis, 2 co-founders of Semiotic. And yeah, I'm quite sure that they won't replace researchers, right? But you're right. And well, actually, I would like that news. If you are on this, I think that I would frame differently that news. If I would be, CEO of IBM, that, with all the respect, I respect Arvind Krishna, but it should be shaped like, oh, we are thinking that, AI will, especially that we are working on that technology, right? That it will empower, it will help you to co-create. It will be like, I like that news better than this, clearly, right? From the point of view of the technology that you as a company are delivering to. All right, so right now you can see that the landscape is like changing rapidly. Some companies and countries like Italy are banning, right? Some others like, hey, Bloomberg, we've got our Bloomberg GPT, right? Like, wow, fascinating, right? You've got your own GPT, your own private GPT, finding on your own data, right? Some companies, of course, want to, yellow AI. I haven't even heard about yellow AI, but the headline is catchy, so I put it in here. NVIDIA, of course. Here's the big winner of the whole thing, right? Like, all right, cool. Here you go. Take all of our software, just buy a few GPUs. And it's awesome. And I can say that as ex-NVIDIA employee, as NVIDIA researcher, I'm super happy, right? NVIDIA earned that, and I'm happy for NVIDIA. So what is under the surface, right? Those are the headlines. So what's under the surface? Is it calmer down there? Well, guess what? It's not. It's crazy too. Just look at the timeline. Right? And I was preparing this talk about evolution. Of course, I wanted to just show you like big timeline from the beginning. I was like, yeah, I cannot show you all of that. I'll need days, right? I will need, I don't know how many days just to talk about it in the details that I would like. But so here's the evolution more or less from just for LLMs. Who knows what LLM is, by the way? Because I'm using that term. All right, so just 2. So let me just give you a heads up. Okay, 3. So it's a large language model. Basically, it's a neural network preaching a large corpus of data, and then it's able. Well, there are a few. I'll be showing you this, but in short, if I look at that tree, it starts in here from encoder decoder model. I will tell you something about this in a second. But basically, there are 2 components. One is kind of processing the input, and the other one is creating the output in a, let's say, generative autoregressive way. And original transformer paper, which was more or less in here, right, had both components, and then the research kind of split. For a few years, that branch was ruling the world, in a sense, BERT-based models and so on. Just you pre-train that whole model on a huge amount of data, on the waste amount of text data, and then you're throwing the decoder out and putting a new one and fine-tuning. We'll be doing that today during the second tutorial. Then there were encoder decoders that were still evolving, and of course, but decoder only, GPT style, like, so they throw away an encoder and just focus on that generative part. Well, as you can see, it's evolving, and I'm not going to show you this today during the tutorial because it requires a lot of computational power to train a decoder, right? And the goal in here was to really just hands-on and train and show you how the training goes, what does it mean to train a model, what are the standard metrics that you're using, and so on. So I'm not going to use this. Depending on the, I don't know, on the interest, maybe we should organize another one. We'll see. All right. So there is clear an evolution happening, right? It looks like an evolution tree. It's amazing, right? So, but is it just an evolution? Let's look at that model. This is very fresh. Llama from Meta, right? Like 2 months old. Like you would in the previous world, you would say, oh, 2 months old, it's fresh. Well, it's not, right? Starting from that paper that Llama was out, people started to derive models, and like there was alpaca, then Dolly derived from alpaca already, right? And then there was Vicuna, and then Berkeley Reese Koala, and in the meantime, people said, oh, okay, Llama sucks because it's not really open source. Let's go with Red Pyjama. I know who heard of the book Llama Red Pyjama, right? Like, so I met the author of this. Like, why did you call that like Red Pyjama? Red Pyjama? Where that name came from even? So no, it's crazy. And look at that. Like those are groundbreaking. Every one of those news is like really, okay, this is groundbreaking new open source model, right? New foundational LLM model. And then you're like, all right, so every week there's a new model. It's crazy, right? It's not evolution. It's like explosion, right? It's hard to follow, right? And each of them has a slightly different properties, behave slightly different way. So really it takes, it's really tough nut to crack, right? To follow all of those news. It's just, for me personally, despite the fact that I'm in that field, I was in that field for 8-9 years just on machine learning side, and in AI for like 20 years. Overwhelming. So I put that slide to calm myself down and you down, right? And let's go back to the main presentation. All right. So in order to work with those models, you do prompting, right? And prompting is the new thing, right? And everyone is saying, oh, prompt engineering is the new job, is the new workforce. And we actually agree. I fully agree. Everyone will have to master prompt engineering if you're using ChatGPT, if you're using Midjourney, if you're using Stable Diffusion, if you're using whatever, right? Whichever of those technologies, right? Generative AI, then you're doing prompt engineering, and you're learning. Oh, if I'll add 4K and great resolution and sunny day and this, it will generate the outcomes will be totally different, right? So it's prompt engineering, and I was thinking, should I give this talk today about prompt engineering? Actually, one of the co-founders, our head of research, who is awesome prompt engineer. Actually, he's poking very much with different generative AI tools, and he's amazing. He's giving a talk right now at the Coinbase Machine Learning and Blockchain Research Summit. I encourage you to, watch that presentation. It will be recorded for sure. And if you want to learn, well, they are better than me to teach you that. There's this open source course by OpenAI together with Deep Learning AI with Andrew Ng, yet another god of machine learning of deep learning. So here's the link if you're interested. I encourage you. Yes.
I just completed that yesterday.
Tell
it's
me.
Really easy to follow, and it's very informative. So I highly recommend it.
Awesome. I highly recommend it too, disregarding the fact that it's on my bucket list to do, right? Oh, this is awesome. I love Andrew Ng. I finished some of his courses on Coursera, like, yeah. And of course, on my pile of shame, right? Of the things that I need to read, finish, Yeah, cool. Great feedback. So I was expecting this, right? So if you're saying it's good, do it. I encourage everyone. All right. So what's the goal of this workshop, right? The goal of this workshop was to go under the hood, under the prompt, and just I asked myself, okay, how to structure this, and then I said, okay, let's maybe talk for a few minutes about what AI is, then what are the paradigms, modalities, and tasks, and so on, and then let's look at the evolution, right? How did really get there, right? And then the second part of the workshop will be like hands-on. We'll be working with few models, and then I'll be, let's say, more open to whatever, explaining you in detail some of the core things. Questions? No. Okay. All right. Oh, by the way, I changed the technology in the meantime. I wanted to start with Kaggle. If any one of you invested your time preparing for this meeting with Kaggle, you didn't waste your time. Kaggle is awesome. I just changed that because I've got some problems with setting TensorBoard. I know how to do it. And then it's like, okay, all the integration with GitHub, and I just went with Colab. I hope that won't change a lot. And there's important bonus of this whole actually workshop. There will be a little bit of critical thinking, right? Whatever I'll be showing you, I'll be also kind of like commenting, right? I think it's important this age or whatever, decade or maybe day of generative AI. We'll see. All right, so let's start. What is generative AI? What is artificial intelligence? Sorry. Of course, I asked ChatGPT what he thinks about this, and I really like that definition: the ability of machines or computer programs to perform tasks that typically require human intelligence. I highlighted that in particular because, well, that's a tricky point. And I'm highlighting it here that we've got a whole panel when we actually discuss that with Annie, with Sam, with some of, it's part of GRTIQ podcast. I don't know whether you know that podcast is the podcast for this ecosystem. I encourage you to listen to this. There is a longer version of what I'll be showing today in the next few slides down there in that panel discussion. So let's analyze that. Which means that in order to answer what is artificial intelligence, we need to answer what is human intelligence. And it's a tricky one, right? Because there is no good definition of human intelligence. Actually, I'm aligning with the line of Howard Gardner, that there is more than one type of intelligence, and there are many premises to this that I think resonate, right? So if you think about intelligent, Einstein, of course, right? Smart guy. But I would say that, okay, Shakespeare was also intelligent, but in a slightly different way, in more GPT way, actually, right? Word smart, can create many good sentences, can create poets, right? I don't think that Einstein could do that, disregard the fact that he was a genius, right? The same goes to painters, sculptors, musicians, right? Or some goats, right? Like Steph Curry is like, okay, he's a genius, right? And it doesn't mean that he's genius in, I don't know, like logical thinking and doing, calculating gradients in his head. He's a genius as an athlete, right? So there's some other types of intelligence, and then interpersonal, people smart, self-smart, like philosophers, right? Naturalists and so on. So my conclusions are, I align with the line of this work, that there are many types if there are many types of human intelligence, then probably there should be many types of artificial intelligence. And the second conclusion is that there must be measured in different ways. And if you look at the progress in, machine translation, right? Neural machine translation, there are some metrics. If you look at the progress in image classification, object detection, different metrics, right? The community is already working on this, right? Like for decades, we were working on different metrics, which actually is yet another indicator, different types of intelligence. All right, so what is AI? So I'm grading right now. I'm moving to the second paragraph. I know, probably you don't see that, right? It's too small. But in short, what's down there, let me read that. Recognition, decision-making, and language translation. Right, and AI systems use algorithms, statistical models, and machine learning techniques to analyze data, learn from experience, and make predictions. Well, so here's my problem. Everything is kind of mixed up, right? And here's how I see that. And of course, if you ask, I think there's consensus in the community. But if there will be Ani, he'll be discussing some of the things that he thinks that are here or there. But in short, artificial intelligence is a big domain, and machine learning is only a subdomain on it, right? In artificial intelligence, you've got truly decision-making, but it doesn't mean that you always learn from data or learn from experience, as in the case of machine learning. And then deep learning is particular a subfield of machine learning, because there are many machine learning techniques, there are decision trees, there's this, there's that. But in deep learning, we mostly focus on neural networks. And here's the funny revelation that when I was learning neural networks back in 2000, 2001, and I was thinking, oh, boring. Well, I returned after almost, 14, 15 years, and like, all right, so we are still talking about neural networks, but what's the difference? They are deeper, right? So of course, there was that huge progress happened in the meantime, right? But at the core, deep learning are neural networks, and that's, you can say that this is not versus, it's equivalent. All right, so next paragraph, once again, let me read that. AI can be classified into several categories, including, right, this is what ChatGPT said. One, supervised learning, where the system is trained on labeled data. Unsupervised learning, when there are no labels. And reinforcement learning, when the system learns to take actions to maximize a reward in a given environment. So those definitions are cool. However, those are not categories of AI. So those are different paradigms, learning paradigms. This is how machine learning systems can learn. And the thing that, and of course, this is a short paragraph, probably if I'll follow up, ChatGPT will give me more detailed descriptions, but those are three classical paradigms. And then there are mixtures of the above, right? So I visualize that more or less in here. And in supervised learning, you've got those labels, right? In training data, and then you train your model. In unsupervised learning, you don't have any labels. So there are a few ways how you can use that. One of them is data clustering, and so on. In semi-supervised learning, there's a mixture of those two. When you're using portion of that labeled data and portion and all the labeled data, you mix those portions, right, during training in a various ways. There's also weakly supervised learning. In short, you start training, you pre-train your model in an unsupervised way without labels, and then fine-tune with the labeled data set. There's also deep reinforcement learning. I won't be talking about this at all, but if you know DeepMind, also OpenAI was doing a lot with robotics with deep reinforcement learning. Today, I'm not talking about that. But I'll mention something about this new powerful paradigm that emerged during the last few years, and actually the revolution that we are observing is thanks to this, right? Thanks to self-supervised learning. All right, so the remaining 2 points that I wanted to highlight is, okay, what are the tasks? So tasks such as visual perception, speech recognition, decision-making, language translation, and then the bottom paragraph. AI has many real-world applications, including natural language processing, computer vision, autonomous vehicles, robotics, and predictive analysis. And we can think about all of that. Like, I was thinking how to classify that, and the natural way is just to look at our senses, right? We've got 5 senses. I won't spend much time on this, but the interesting question that I want to ask is like, okay, where the language falls in, right? When I talk, you hear me, you hear the language, right? When you read, you see the language. What is language, right? And it's intriguing from the point of view of machine learning, and from computer science, because language is something that, that is the natural modality, right? The text is natural modality, well, just right above the, zeros and ones, bits and bytes, right? So let's focus on those three modalities, and I just wanted to show how they map to different tasks, and that we are using machine learning, we are using computers. I'm quite sure that plenty of you guys got all those smart TVs, smart speakers and whatever, smart refrigerators that talk to you, right? Or listen to your commands. So sound, vision, language. So basically, sound and language, this is kind of like the field of conversational AI. Vision language is more the field of, let's say, generative AI. So what are the mixtures? So what is speech recognition? Actually, it's speech to text. When we are starting to mix those those modalities. Speech synthesis is text to speech. Image classification, image to text, it's label. Image captioning, well, image to a description, right? Image synthesis, text to image, Midjourney, that's one example. Video synthesis, text to video. Stable Diffusion has quite good models for this too. Text classification, text to text. We are just putting a label, right? That, okay, this is let's say, this email is a spam or not, right? It's a classification task. Text summarization, of course. Hey, ChatGPT, summarize me something. I'm doing that all the time, right? Machine translation, text to text. So when you are translating from one model, from one language to the other, then dialogue, actually, it's also text to text. ChatGPT is in the previous version before GPT-4, because this one can also read, you can input images. I'll tell you later about this more. Basically, it's text to text with that asterisk. And then visual questioning. Okay, so we've got image and a command expressed in natural language, and then the system is returning some text, right? Some answer. I put in here some other crazy things like Antonio Torralba. So we are kind of collaborating with him back in the IBM research days, and he's doing like crazy stuff when it comes to vision and hearing, like vision and sound, like, imagine kind of hallucinating sounds for different videos, and totally different sounds is disturbing. Very fascinating line of research. But so, it goes and on and on and on. All right, so we've got I think the foundation. And that was the core, the first part of this talk, actually second with the news. So now let's go into that evolution. I really spent most of my time preparing this part. Oh, and we are good when it comes to time. So questions, anyone, like about the first part, about the, I don't know, taxonomies that I've presented and the foundation. Anyone? Or am I too slow, too fast, or? All right, cool. Yes, they will be. So the notebooks already are, and the slides, I just wanted to collect maybe feedback, polish them, and then I'll export them to PDF and put together in the same repo. All right, so that's why there are some links down there that, just few. All right, so those slides, I've got 4, but are very heavy. I already said, right? I wanted to show you that, give you more, let's say, fundamental stuff. I wanted to show you evolution from the point of view of evolution of architectures, of neural network architectures, but I gave up. Like, in a sense, I said, okay, I need a better tool to draw what I have in my head, and I stick with this because there's a lot. And I want to start from actually prehistory, right? I want to start from the very, 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 very beginnings, because it dates more. If you know, there was this workshop in Plymouth in when they coined the term artificial intelligence. Guess what? Neural networks are older than this. So the first neuron model was called Pitt's model. It's very simple. It's just few inputs, weights, and then output, right? And then they were showing how to connect those neurons together. So they were like sharing inputs, and then there were a few outputs. There was no training algorithm for this, but they were saying, oh, this is a simplified brain cell. Actually, it was. It kind of like it was the foundation. Then Rosenblatt, actually, he used that and proposed first artificial neural that could learn. If you hear nowadays about MLP, it's multi-layer perceptron, people are mixing things because perceptron had a particular way of learning. Right now we are using backpropagation that I'll tell you in a second. Perceptron wasn't using, but it's basically common name right now. People just adapted that to represent when people are saying that they're thinking about feed-forward neural nets, right? Like multi-layer feed-forward neural networks, MLP. All right, the next big step, and actually it was like a showstopper, was the book by Minsky and Puppets, Perceptron, when they criticized the architecture. The whole book, okay, they were discussing many things, but at the end, the result was the big limitation and the big use case that they were showing that, oh, with single neuron, you cannot, with single layer, you cannot solve even the XOR problem, which is true. But it's not true if you've got multiple layers and non-linearity between them. But that book resulted in kind of it stopped research for a long time. Still, there were some people pushing, and Paul Verbos was one of them. He came with this, or maybe he applied backpropagation because he didn't discover backpropagation. Backpropagation was there. In here, I had this link to Jürgen Schmidt-Huber paper called Deep Learning from Neural Networks. That paper comes with 888 citations. In some of them, he's referring to the original citations about on backpropagation. So anyway, Paul Verbos came with the core algorithm in his PhD that is used right now for training machine learning models. So look at that, 74, wow, fascinating, right? 50 years almost ago. And in here, I just highlighted one model that was quite interesting, that it can calculate neocognitron, laid the foundation for CNNs. And of course, you know Jan LeCun, one of the Turing Award winners a few years ago for deep learning. It was him, Hinton, and Bengio, Joshua Bengio, right? He was working on for a few years at that point, but in 1998, landed 5chem. It was groundbreaking because he have shown that actually he deployed that. He put that model in production. That model was recognizing digits, and that was one of the core idea of the tutorial. He put that in production, and it was like in all of those, ATMs when you were putting checks, it was recognizing, the digits down there. So great improvement of, of automation and great, application, right? And he have shown that it can work. And it was that's why I highlighted that with that red dot. Aside of architecture, like convolutional neural network, it was following up more like, let's say, human visual system. There are some filters that are reacting to different patterns that are trained, right? Convolutional neural network is one of the foundational architectures, right? So in here, actually, there are two things that are worth highlighting. What happened in the meantime, Hinton, another from the big trio, Ramelhart, Hinton, and Williams, applied backpropagation to train multi-layer neural networks. And of course, Jan LeCun leveraged this and leveraged that. But it was great groundbreaking. Let's say it laid once again the foundation for the next progress to come. Verbos was continuing working on backpropagation, of course, not all the time, right? I don't think he worked like 12 years exclusively, but in 86 he proposed backpropagation through time, BTT. That became the algorithm for RNNs, recurrent neural networks. Once again, without the slides on the architecture, maybe it's hard to who knows what are RNNs? Maybe who heard about RNNs? Oh, all right. Maybe I should put that slide. But in short, okay, who understands recursion? Right, I think everyone in this room should understand recursion, basically. So now imagine that you've got a sequence of inputs and you want to somehow, put it together, like make some sense of it. So the way RNNs works is that you feed the first element of that sequence, and then it produces a hidden state, kind of like not the output, yet another output, right? There's output and hidden state, and that hidden state is fed back to that neuron, to that cell, or to that layer, right? With the second token, and then with the third token, and then with the fourth. So the last hidden, so in that sense, you can aggregate, compress, let's say, the whole sequence. And RNNs had issues, even with BTT. People realized that they're struggling with problems, with very elementary back then problems, that were called vanishing or exploding gradients. So when the sequence was long enough, the gradients that were When you train a neural network, you do the forward pass, right, with the inputs, and then you've got the targets, right, in supervised learning. And then, so you calculate the difference between what networks outputs and what network's supposed to output, and you backpropagate through that. You backpropagate gradients, and those gradients are used to improve the weights of neural network, weights of each layer, weight of every neuron. And if with RNNs, with long genome sequences, those gradients are vanishing, means that they become zeros. Like, the neural network wasn't training, the lower layers weren't changing at all, right? Because at the beginning they were close to the output, they were big, and then they were like just vanishing. Or the opposite, they were just exploding, right? Like becoming big, and not a number, and boom, training failed. So long short thermomy, actually, there's a red dot because it was another groundbreaking architecture in the late 90s, because it's a special type of RNN that mitigated those vanishing and exploding gradients by introducing gating mechanisms that became very important mechanisms for the gating on its own became very important. And also LSTM became very important because up till for 20 years, it was running all the applications. Like really, if you've got machine translation, it was based on LSTM. If you've got up till, let's say, probably 2017, 18, 19, right? So 20 years of really sole rule, right? This architecture was super awesome. Schmidt-Huber is yet another godfather of deep learning. Right, speech recognition, all the sequences with text, with speech, super awesome. All right, so I will fast forward now. I kept like more than a decade of research for a reason. It's a lot, but I wanted to highlight some of the most important things in CV first, then in language, and then in multimodal. So, ITSA, where Schmidt-Huber is from, well, not he's from, he's the director. In 2010, they have shown that you can use GPUs to train, neural networks. That you can train deep neural networks, deep. Okay, maybe not that deep as we are thinking today, but let's say like 5-7 layers. And it laid the foundation for the next kind of groundbreaking, like history moment in machine learning, together with ImageNet, right? So Faith Lily was working from Stanford back then, and she's right now in Stanford, but she was with Google Cloud for a few years. She worked for, actually, there's very amazing talk how she was working on ImageNet. It was first large-scale data set for computer vision, for image recognition. Few approaches. At the end, she used mechanical Turkers and created that huge data sets and founded the challenge. And in 2012, Krzyzewski, Sutskever, and Hinton won the ImageNet competition with their deep neural network called AlexNet. And that was the groundbreaking moment because first, they won by big margin, and second, that was the only model that was actually running neural networks, and they didn't know much about computer vision. They just knew a lot about machine learning, and they just crushed the competition. People who are working for decades on dedicated solutions, right? And computer vision community, that was, they've made a big whoa. Like, how did that happen? Those guys, they do not know how to build filters, how to build those different processing pipelines, specialized. They don't know much about, SIFT transformer or whatever, right? But somehow they won. How is that even possible? So what they knew though was how to train, neural networks, convolutional neural networks on GPUs, right? And of course, Hinton was already, like 3 decades in the field. He knew a lot, right? And he had very smart student, Alex Krzyzewski. I think he's still with Google Brain. But Google Brain just few days announced that they joined with DeepMind, so it's Google DeepMind right now, I think. And Sutskever, well, okay, OpenAI, so where Sutskever is, right? So then there was a series of groundbreaking models that were running year after years with more and more and more deep learning, right, appearing. So 2014, GoogleNet, once again, from Google, right? At that point, after this, they were hired by Google, by the way. There is a very interesting story behind this, but I won't tell you, just Google it. Right? And they introduced inception model, which basically was like a module with different convolutional layers inside of it, with different connected in various ways, with 1D convolutions, 3D convolutions, with 5D convolutions combined. And actually, the model was quite deep. And once again, so they have shown that with combination of few smaller convolutions, you can get better accuracy or on-par accuracy with large convolutions, which are more parameter hungry and they require more computation, right? So that was kind of like a big improvement. It was more efficient architecture. Then, and they of course they won, right? Right. Then in 2015, actually, residual networks appear. ResNet, once again, Google. And ResNet actually introduced something that is in here. I called it shortcut connection, but it's called residual connection. The name ResNet comes from the fact that it's residual. So you can think about that there are, let's say, there are 3 layers, and normally those feed-forward layers are connected from layer A to layer B to layer C. Residual connection skips the layer in between. So it helps. Actually, what it's doing, it's helping the gradients to backpropagate. So once again, you can stack more. And we already learned that from this paper. In this paper, there was this actually residual connection, but controlled by gate. In here, there was no gate. It was hard-coded. Then actually, Schmidt-Huber released a paper called Highway Nets when he generalized over those 2 approaches and proposed feed-forward networks with gating mechanisms that, in one case, were really residual networks, right? So once again, there is a mixture of, I'm already showing you how those 2 influence each other on the architectural level, those 2 domains, language and vision. I will show you more later, right? That's kind of at the core of this talk. All right, so 100 layers, right? Of course, winning the competition. What happened that year? Also, region CNNs appeared, right? Before that, neural networks were used mostly for image classification, so you need to tell what is on that image. Is it a cat? Is it a dog? Right? And then people start thinking, actually, life is complex. These are more complex. There are chairs. If I'll take a picture of that snapshot of that room, right? I'll see plenty of people. I will see tables, chairs, right? Windows, whatever. So object detection, it's important, right? And first region CNN, then faster, and so on. So Ross Gierschik was making huge improvements in here, starting from basically using CNNs, and the core idea down there that he proposed a solution called region proposal network in fast RCNN. So first he was making some soft hypotheses about what are the bounding boxes surrounding different objects, and then passing all of them through CNN, through a convolutional neural network, which means that it wasn't efficient, but it was working, right? Because you were having many passes, right? And then he, of course, faster, he improved that, and so on. But then YOLO appeared, and I remember that was, I think, on CVPR back then, or was that on NeurIPS? I think on CVPR, it was a keynote talk. The difference was, well, once again, we are using neural networks for object detection, but guess what? One pass only. They kind of flip the idea. So first you're doing one pass, collecting all the features, and then on the feature level, you're doing those kind of you're trying to see which features are forming which regions, right? So they flipped the idea, and I said YOLO. Right now, I think it's YOLO V7. It's content. Those are years and years, and those guys are still progressing, building next versions of those architectures. But it's a fundamental architecture. Then what appeared was Mask RCNN in 2017, and it was awesome because at that point, semantic segmentation became possible with neural networks. Semantic segmentation means the difference between semantic segmentation and object detection, that with object detection, you've got bounding boxes. With semantic segmentation, literally say on a pixel level that pixel belongs to that class. And moreover, what you can also do based on this, you can do instance segmentation, right? So if I'll have, like, let's say the pixel of you 3 guys, right? Like if I'll take a snapshot, the old models will classify all of you as one person, right? With instance segmentation, I'm saying this is human, this is human, this is human, this is chair, right? It's more fine-grained. Right, great architecture. Once again, Google was pushing very hard. And in 2015, like Sutskever left Google and formed OpenAI. There are no advances from them yet. Right, now let's switch gears to NLP for a second, and I'm starting from slightly different moment. They were like, let's say the most important things happened, I think, starting from 2013, and of course, there was progress in the meantime, right? But in 2013, Thomas Mikolov, he wasn't with Meta, but then later he joined Facebook. He developed word2vec, which is, here's the problem that NLP domain, natural language processing domain, was facing. Imagine you've got sentence, right? People were, in order to pass that to a neural network as input, you need to turn those words into some kind of numerical representation. So one of the elementary representations was called one-hot encoding, which basically means that you create a dictionary of all the words that that are in a given book or whatever in your data set. And then one word is represented with 1 on this long vector of, if you've got 30,000 words, a vector of 30,000 zeros with 1 is created, right, for a given word. So this is not efficient representation. What word2vec does is they said, oh, actually, once again, maybe similar to computer vision, maybe instead of doing feature engineering, we'll try to learn those. And the idea was, in short, that they created that matrix, right? And they were like trying to represent words with vectors depending on the frequency of their appearance. And I'm simplifying a lot because actually inverse frequency, and there are some let's say there are some more complex thoughts down there. But the idea is that at the end, each word was represented by some kind of vector that wasn't that long, but instead was a dense vector full of floats, right? Which was very, very powerful idea, especially that you were training that for your data set, right? So it was creating compact representations, 128, floats or 256 floats, something that was tractable. Then in 2014, 2 things happened actually. First, sequence to sequence. Sutskeber, once again, he was in computer vision. Now I'm showing you another groundbreaking thing. I should put red dots everywhere. It's quite hard to, right? I'm biased. I've got my own bias. The red dots are my bias. Probably I'll ask. Yeah, I asked ChatGPT. It has his own, vision on the most important things, but we agree on in many cases. Anyway, sequence to sequence. What was the core idea down there, and what was applied for? It was applied for machine translation. So I was already explaining you. It's text-to-text problem. So the question was how to do it efficiently, and the core idea was super simple, natural. Let's use one RNN with embeddings coming from one language, right? So there are words in English, embeddings, English embeddings, vectors, and RNN is aggregating all of those, right, in a recursive way. We are creating that dense representation, that hidden state, and passing that as input to second neural network that operates on, let's say, German embeddings, and it creates outputs in German, right, by unfolding the neural network in an autoregressive, in a generative way. Autoregressive, maybe one word of explanation. Who heard that word, autoregressive? I already said that twice, so you did. All right, so autoregression means that when you're generating, when that second neural network that generates is generating a word, and that word is fed as input, as input for next word. So thanks to this, it's like you're writing, right? Like you're looking, oh, I did this, oh, I did this, oh, okay, right? That's the idea. And there are special methods for training autoregressive models. There was also huge progress down there from Joshua Bengio, like apprentice learning, teacher forcing, and so on. I won't mention this, but sequence to sequence appear to be very, powerful paradigm. Basically, this encoder decoder with RNNs, and became the foundation for machine translation. Google Translate was working on this for a few years, until one thing happened, right? But for a few years, it was very powerful. Moreover, what Banadao from, once again, Bengio's lab, from Mila, he introduced a mechanism that in the paper it wasn't called attention, but later everyone talks about this as attention. The idea was as follows: so you've got those 2 sequences, inputs and outputs, right? That outputs that you're generating, and then instead of just passing that hidden state, the decoder can look at all the inputs, at all of them that are already processed by the neural network, right? And say, actually, for this output, by looking at my current hidden state, I'll take 3rd and 5th input and create a thought based on those 2, right? So it's like for every step of generation, it can cherry pick to which word to pay attention. And if you'll translate from English, I know that from that paper, remember, Do you remember, Ahmed? There was this this drawing with a translation from English to French, and there was like a European Union and how is European Union in French? Excuse me. Right? So you flip those words, and guess what? It could do that efficiently because it was paying attention that, oh, actually, you know, European appears in the context of union. So first I should return l'Européen. Yeah, yeah, as he said, right? But there are many cases like this, right? It just could capture those dependencies between words. It became more contextual. It was very important. Google Machines Translation, as already mentioned, I'm putting that in here because, you know, everyone started to use Google Machines Translation and nobody really, you know, it's open source and it was amazing, right? From 2016, it was amazing. Then in 2017, those guys from Google Brain, can we that architecture called Transformer? Who heard about this? All right, 4. Well, those 2 guys should also raise their hands. So here's a funny fact. We invited the speaker, one of the authors of that paper. That paper was released in December 2017. In January 2018, we had him in IBM Research and look at that. Oh, that's super interesting. Yeah, but we'll work on our multimodal. We were doing multimodal research back then with vision and language and with reasoning, with memory augmented neural networks. Yeah, that's cool, but yeah. And at that point, you know, that was for text only, right? Anyway, then, let's say we misjudged. The impact of transformer is huge. I think that dot should be, I don't know, the size of the screen. It's amazing what it's really progressed a lot, right? Because what they did, they introduced a new mechanism called self-attention. They built this architecture once again, encoder, decoder. Both of those were. The idea was that, okay, RNNs are bad, so the encoder will be feed forward. How to then pay attention to all of these different tokens. And what self-attention enabled, actually, it enabled to produce something called contextual word embeddings. If those were word embeddings that were like looking at the context of one word or one token, then contextual word embeddings, it was creating the representation, that vector representation, not only based on that word, but also of the context of that word. And you know, this is very important for the language because you've got this ambiguity, right? The same word in different sentence can mean something totally different, right? And transformer enabled that, right? Enabled to the neural network to learn that in this context, this word should have this vector, and in a different content, it should be a different vector. It's super powerful. Self-attention was very powerful. It's very powerful architecture. And it was a groundbreaking. Of course, they did that for machines translation. Starting from that moment, Google started to switch to transformer. LSTM kind of started to fade. Right, people started to switch to transformer. And the next year was like, I think it was a year of whatever former, right? It was conformer, long former, like hundreds of variations of that architecture with this and that. But moreover, in here, as I previously said, okay, it was encoder decoder. People start to experiment. Oh, we can only maybe if you'll pre-train that. What can you do with pre-training, right? And NLP experts were looking at what is happening with computer vision, right? Because since ResNets, people start to say, oh, we can pre-train that on ImageNet. It costs a lot. But if we'll just throw away the last layer and put a new one or a few new ones, so once again, encoder, decoder kind of a style, right? So we are throwing decoder and putting a new one, fine-tuning. Oh my God, it works. Actually, I will show you that today. We'll play with that. I'll give you proofs that it works, right? And NLP guys said, can we do the same? You're already doing that with kind of like a word embeddings, right? There's GLOV, after word to vector, there are other approaches. I should mention GLOV, actually. But like, okay, can we pre-train that? And this is how BERT emerged. The BERT emerged from this idea that, okay, maybe we can take that transformer, pre-train all of that on huge corpus of data, throw away the decoder, and fine-tune that on different data sets. And they have shown amazing results, I think, on 6 NLP data sets, super different tasks. They were state-of-the-art. And that was yet another groundbreaking moment. Whereas at the same time, yet another paper appeared called ELMO. The learning paradigm that they used, because it's very important, they use self-supervised learning. I'll I'll say in a second how that worked. But Elmo was based on literally the same ideas, but different architecture. It was based on LSTMs, right? And it was super cool, but Elmo kind of faded and BERT stayed. And after this paper, it was Roberta, Wilbert, and all kind of, I don't know, variations of BERT, right? That emerged, that started to emerge. And here's the self-supervised paradigm that they used. Actually, they've got few tasks, but let me just focus on one of them. What self-supervision means? You don't have the labels, right? But what can you do with text? Well, you can do the following. You can mask one or a few of the inputs. You've got a long sequence, and you can pass that through a neural network and say, hey, what do you think are the missing words? If you do this, you don't need labels. The labels are coming directly from data. What you're doing, you're masking, right? What the model is learning, contextual context, and it's learning dependency between words, right? At that point, you can turn any text into data set, right? So that was very powerful for language. People start to build more and more and more and more, and like bigger data sets. And it appeared to be super powerful paradigm, right? It really, that thing is called the ImageNet moment for NLP, really, because people are like looking for that groundbreaking moment, and I think this is it, right? There's also like a the ImageNet moment for speech, there, but we won't talk about this, right? But the ImageNet moment, it's quite funny. All right, so this is more or less what happened during those, well, I don't know, 5 years. Oh, I forgot. One tiny element, GPT, right? So OpenAI wasn't sleeping, right? Like they were working hard too. They were working on few things. They were working on robotics. Like I know all of you saw the results when they are like manipulating first cube with hand, and then solving actually Rubik cube with one hand. Have you seen that? Dota, like video games, deep reinforcement learning. Anyway, they also working on text, right? Of course. And they dropped a paper called GPT-1 when they, instead of doing that mask language modeling, they said, okay, let's predict next word. The most important thing that both those paradigms were present already back in the days, right? People know that. But in a large scale, that appeared to be super powerful. So in here, they focus just on that generation, they just took decoder, right? They're treating, past input tokens as kind of like already kind of generated. They're already generating them, and then generating the remaining ones too. So it's just generative decoder, and the task is next token prediction. So what they're learning, once again, huge amount of text. It's like, okay, what do you think will be next token? What do you think will be the next token? You can train. Once again, it's semi-supervised. They call that in the paper unsupervised. Now we know it's semi-supervised. Second very powerful paradigm. And let me go briefly. Okay, I knew. I was very fast with the first slides, and then the 2 slides, half an hour, right? Or 3 slides. All right, I'm almost there, so 2 more minutes, right? We started late. So in here, what I wanted to show you was that actually, when people realize that, oh, there's vision and there's language, and I was one of those guys, and actually my colleagues from Semiotic were the same. We're like, oh my God, you can combine them. It's amazing. What will happen if we will combine those 2 modalities, right? So of course, first thing, Karpati. Who heard the name? I guess some of you did. Nice. He's once again back with OpenAI, right? But that many years with Elon, fascinating. I respect the resilience. So he worked on, once again, encoder, decoder, but in this case, the encoder was image and the decoder was RNN, right? And oh wow, we can generate captions. We can actually describe what's down there in a text as a sentence. Fascinating, right? So the core concept down there was that visual semantic alignments, that different tokens were referring to different elements of the image. Very, very cool work. At the same time, people from Facebook AI Research, Georgia Tech, dropped the visual question answering data set that they caused some chaos with that, because they should literally call that image question answering. Our life would be easier, because it was all about image recognition, in a sense that you're asking what's on that image, or what the man is doing. Is the man wearing, what is the color of the hat that the man is wearing, providing the image, and the system was supposed to provide some answer, right, in text. So very, very interesting data set. And then few advances, those were mostly on attention. At that point, we were also working on attention a lot. We are doing also research. exactly in that field. Then BERT for VQA appeared. I'm just highlighting that it improves. But two important things that happened were in 2020. I'm skipping a lot, trust me. There was a lot happening. One of them, vision transformers. Those guys realized that, oh, we can do the same with images, with transformer. We can split that into regions. We can encode it of those regions as a vector. We can turn that into a vector. And with special additional positional encoding, oh, actually, you can learn that encoding too. We can pass that as a sequence to transformer. And that appeared to be super powerful. Once again, self-supervision for vision and architecture from language to vision, right? So those two, are, as I said, were fueling each other. Then 2020, the PAL. Without the PAL, we wouldn't have, ChatGPT, actually. Huge data set, huge comprising of bunch of other data sets and 10% of world's internet and this and that. Huge data set, 800 gigabytes of diverse, text for language modeling. Then one important point in 2021 clip, right? When once again they kind of followed that, and it was contrastive. They were learning embeddings for language and text and trying to make them closer by using contrastive learning. DALI, okay, extension of that generative, pre-trained encoder GPT, but for images, why not? Very, very simple solution, and guess what? It's a very good product, right? And then Stable Diffusion appeared. It's based on a slightly different approach. It's based on variational autoencoder with the use of actually UNet architecture. I haven't mentioned that. But once again, what I'm showing you at the end, it's kind of fascinating that plenty of that research was done in Google, in Facebook, in some of them in academia. But now what we are seeing is that those companies are, the startups are really, driving that innovation. It's fascinating that if you'll go to AI conference right now, you won't hear plenty of the stuff that you're seeing what are appearing in the products in generative AI space. For me, as a researcher, as a guy with 15 years in academia, I'm in shock. I'm mind blown. All right, so let's summarize this. We are a little bit late, sorry for that. So, okay, encoder, decoder, sequence to sequence, very powerful architectures, and they really kicked off that the whole generative, AI boom that we are observing right now, more than a decade of research, right? Like hard research. Progress of neural networks for computer vision and NLP influence each other. I really wanted to show you this, right? That, if you're looking from your narrow perspective, you won't see what is happening down there. That's why that's one of the reasons why I really got into conversational AI. I'm a computer vision guy, but last, 6-7 years, I was really learning and doing research in NLP. It's fascinating. I never could predict this. Then self-supervised, pre-training, groundbreaking discovery, really. Like the fact that we can leverage all that data without any labels, yeah, that's a bomb. Two powerful paradigms, like down there, like mask language modeling, BERT-like, and next token prediction, GPT-like. Yep, worth noting. Finally, okay, we wouldn't do this without all of that data, right? And new model architectures, and of course hardware. Thank you, NVIDIA. TPUs are great, but I still think GPUs rules the world. All right, and that's the end of this part of the workshop. So questions? That's a good question. Let me answer this. No. All right.
I didn't fully understand why next token prediction was so transformative.
Well, the task is easy, right? I remember Hinton and Berger had a paper in like 90s showing this task. It was transformative because of the data that appeared, right? What they're actually showing, if you read carefully, or if you listen to Ilya Sutskever or guys or folks from OpenAI, they're saying, okay, we took something that we're thinking is simple, but we push that to the next level, right? With large-scale training, with large of data, and it's like, oh, magic appeared. Actually, I have shown, maybe I'll add a link. I need to take a note. There is this Michel Boubec, guy from Microsoft Research, he's leading the AI Foundations team. He gave few talks about emergent properties of large language models when he's showing that, okay, the same model, the same architecture. If you're training that on that much data, this is how good it is. It's not good at math, it's not good at this, it's not good at summarization. If you increase the data set, right, and number of weights, oh, it's getting better on this, on this, on this. And at one point, it's just new abilities are emerging. At one point, it's starting to count, like it's starting to do logical reasoning, multi-step chain of thoughts kind of reasoning. It's like, how did that happen? So powerful architectures, new transformers are very powerful in a sense that they can store a lot in their weights. Like we are talking about models, like Palm model is 540 billion parameters. It's a huge model, right? Today we are going to train BERT, who is like, I don't remember. You'll see that in the notebook, I think. But we are going from tens to thousands to hundreds of thousands to millions, and now we are on the order of trillion, right? Of course, it's not in production, right? GPT-3 had 175 billions, and it's all about the learning paradigm is super simple, right? But to make it work with such a big model and big data, that's a lot of engineering, right? And it's intriguing, right? Like I'm saying, those two paradigms weren't like the ideas behind them were there already in the papers. They just took it, applied, flowed with data. It's just, God damn, it works, right? And those are two. I'm emphasizing because those are kind of two different ways, right? And one is more for training, as you will see today, like decoder, like encoder style solutions when you just pre-train and then fine-tune your data on your specific task. The second one is more towards generative decoder, right? That next token prediction, because this is how autoregressive decoders work. Pleasure.
I'm just curious, as someone with a computer vision background, what excites you with the latest? Like, is it something like segment anything, or?
Yes, that's super cool. I was shocked by this one, actually. Really good. Yeah. The line goes on and on and on, right? And spreads. No, I really think that, okay, when I joined NVIDIA, I've joined conversational AI team, and I was trying to push more towards this vision plus language stuff. But I've joined because I wanted to work with experts who actually know a lot about NLP, because I was thinking that something like search supervision will be important for computer vision too, right? And at VIT, yes. That's one example, right? And it's more down there, right? So it's all about looking. Yeah, I'm not really answering your question. What really excites me in pure computer vision now? God damn, it's a tricky question. Yeah, but for sure, Sam is awesome, right? Like.
Yeah, some of the latest stuff like OpenAI, they're doing this cool kind of private data with Be My Eyes, which helps just blind people.
I haven't even heard about this.
But it's a really
Super cool.
use case of computer vision where one person can point the camera at something like a fashion magazine, and then the LLM will help interpret like this is not smart.
Yeah. So, but do you consider this as pure computer vision? Because for me, it's multimodal, right? Already, it's just vision and language combined, and I really think that's super powerful paradigm. And right now we are seeing emergence of some of the tools and projects that are like already like they've got how many, like I was reading that there's like 20,000 people using daily Midjourney, Stable Diffusion, and that generative AI for images, right? Those portals or websites. Right, the impact of that is mind-blowing, and actually it's text plus vision, right? Because your input, you prompt with natural language and you generate images, and I'm, expecting, systems, all kind of versions of that, of those mixture of those two modalities will appear. That's why, like I was like, hey, multimodal machine learning, this is powerful, right? Not only from the research side, but applicational side, right? Yeah, this cool, good question.
About the opposite, are you concerned about AGI and?
No. Right, and here's the deal. So I've got background in robotics. I did my PhD in robotics, and my answer as a robotician is as follows: as long as the robots are flipping when they're trying to grab the knob, you're safe. They won't, right? You're safe with that. But of course, there's huge. Now, serious answer: the impact of GPT-3 of ChatGPT basically on society is mind-blowing. Like mind-blowing. When that was released, I remember December, January, I was flooded, like all people, like my friends from Poland, from the US, people not knowing anything, not doing anything, not having anything in common with AI, were like, hey, I did this, hey, I have about, like, what is happening, right? I was reading about, first thing as a teacher, as a, you know, I was adjunct professor for 4 years, like, God damn, now, how do you grade people, right? Like, you're giving them homework, and like, how do you know that they did that? Okay, the whole paradigm is shifting, right? We at Semiotic first like, okay, we should ban our interns and our new employees from using generative AI, from using Codex, because there are some tricky things with the license. And then after a few months, I said, listen, we need to revise that policy, because it makes no sense. First, we are a first company, but second, really all the new people coming to the market will be using that. It's like, are you using IntelliSense in your software development? You are, right? Now you will be using, you know, Codex. It's just natural. It's there. It will be embedded in every tool. So we need to come up with new policies, right? So the market is changing. The employees are changing. I'm listening about companies who are trying to use that to change, to optimize processes in their companies, right? Today, protests on the streets. I was hearing that the writers were protesting. Like, someone sent me the news, but I was driving, so I didn't read the whole thing, right? It's big, right? It's really the impact on the whole society is changing. And as part of this, you'll see that especially in the second part of this workshop. What is important is critical thinking. And I was mind blown when in Wired magazine, I think from February, there was this news, not news, article about a teacher. I know, like, I don't remember which state was that, but she was in shock in December when ChatGPT arrived. She had exactly the same concerns, like, well, okay, all the teachers are right now doomed, right? So what can we do? Oh, so they banned ChatGPT in their school. So what she did, she used their own hardware and created during the Christmas period some course with their students, where she was like, okay, let's use ChatGPT, and now let's analyze that and let's criticize that. Let's see what it did wrong, right? Let's do fact checking, right? And she's teaching that kids, and it's awesome. I think this is the way. I think she should become like a minister of whatever education, right? Because she sees the problem and thinks that the next generation will be struggling with this a lot, with deep fakes, right? With fake news, with very personalized. Everything will be super personal. I personally believe that, you know, there will be like Tom GPT, your GPT, right? Like, everyone will have its own GPT running maybe here, right? Well, it will be your personal, you know, guy, but you need to learn what is good for, right? Maybe it's not the best for facts. When I was preparing this, trust me, I was also operating. I can show you prompts like, oh, wait, that paper wasn't from this year, because I remember that paper. I was going to Google Scholar. Yeah, I'm right. It's wrong. Still, those are good points, right? But for fact checking, it has a huge impact on society. And European Union coming with regulations, US people, you know, government are working on some regulations. It's very interesting what will happen in this space. But one thing is clear, it's going to have huge impact, right, on workforce, on how we work, on how we live. It's amazing. I mean, like, trust me, when I was leaving NVIDIA, I was working with team who was training actually the Megatron. At that point, that was the biggest model, 540 billion parameters, Megatron NLG, right? Microsoft put a big logo on top of the, they are playing the game well, right? But it was Microsoft and NVIDIA collaboration. Actually, we're training that model. Yeah, when I was leaving, I was thinking that in a year, something like that will happen, right? It's just, I'm mind blown, right? And I'm excited, terrified. I don't know. My emotions are all over the, you know, are all over the place.
So you gave a pretty cool, like, detail of like the key things, but if you leveled it up, like, what's a core primitive concept that you think is moving things along? Like, I read someone who sort of described how the generative adversarial network.
Yeah, I skipped that totally.
Fundamental shift of applying the networks sort of against each other to create this.
Yeah. Very good question.
Leveled it up. Whereas I get, like, the way you did it was like, oh, it moved forward, but like, to me, like, I started when it was learning the back propagation, which I thought was like good, and I think they still use it, and so. But it
Me too.
Enough, and so it was like,
I did that on paper. I remember when I was learning that to do that on paper in school, right? Like at my university back 2000, 2001, right?
Oh, yeah, we had a
Then,
yeah.
yeah.
We tried using Mathematica.
Cool.
To do it, but,
Awesome.
But like to me, like that's like an idea, which was like, okay, here's
Correct.
going to be gradients. Why? Because you're going to
Yeah.
adjust the thing. And that's like a core idea. And then another sort of core idea was you have adversarial networks, and they're just going to just. And when I read the paper that explained it at the level, I was like, oh wow,
Jan,
really advancing it. In a number
Jan's paper, the original paper.
I read about it on paper.
All right, so here's my comment on GAN. First, if you read the comments by Schmidt-Huber, he's always saying, oh, I invented GANs before they were famous in 90s. And it's true, actually. He came with similar concepts, right? So when Goodfellow came with this, it was mind-blowing because it was for unsupervised learning, right? They've got their moment, right? And after GANs, there was like big GANs, cycle GANs, disco GANs, like hundreds of GANs all over the place. And I think that the concept on its own, that you've got generative that they've got generator and discriminator that are playing that adversarial game, is powerful, but it's not celebrating those successes in here, right? Like the boom that we are observing is not driven by this. But of course, it's a very important piece. For me, like I said, this, once again, self-supervision on, GANs are unsupervised. People are still figuring out what unsupervised means, if you think about that, right? If you read the original, like GPT-1, GPT-2 papers, and plenty of papers like that are trying to address this kind of like a not supervised, but semi-supervised, weakly supervised, self-supervised, right? They're trying to capture what's the essence. For me, what I put in here, that's important. Right, those two paradigms, very simple, right? You understand them at the very core, right? You've got the sequence, and then you mask it, right? Or you say, okay, predicts the next token. You've got the sequence. You're not doing not much, but why those paradigms are powerful. The same goes to GANs. With GANs, you could do that with literally every data, every image, right? You could start generating that, right? But the GANs are a very interesting architecture for sure. I'm not saying no. But this is more powerful. Once again, semi-supervision, right? Self-unsupervision, right? Something that will enable you to make sense, to use more and more and more data, right? Because what is costly? Labeling, right? And of course, I haven't mentioned here a very important piece, that there is reinforcement learning and human feedback, behind ChatGPT. That what I will be showing today is how to pre-train, but then you fine-tune. And there are very important pieces of research. For me, the most powerful, most interesting technology right now that actually is coming from OpenAI, that right now they're kind of hiding that behind doors, is RLHF, right? Reinforcement learning with human feedback. And I'm not even mentioning that in here because that should be like another huge talk, because there's more than this, right? DeepMind with their Sparrow, they've got slightly different ways of fine-tuning towards learning from human preference, basically aligning the model to be more compliant. And I think it's going to, yeah, it's very important, right? Especially with that explosion of those foundational models. I'm calling them base models because they're trained with those paradigms on huge piles of data. Now, how do you make sure that it stays with those guardrails, right? Like, you don't know. Yeah, so that's a more philosophical question, right? For me, well, I tried, right? It's from high level. When you're doing research, it's good to look around, right? So I was CV, and then I started looking at NLPs, like, wow, nice. So can we take something, from this different domain, right? So that kind of like that influence, it's important, and that's my second high level, and that's, well, deep learning core, right? Like fundamental one-on-one, like, oh, more data, better model. Am I answering?
I'm good, yeah.
Can you repeat what that new field is that you're talking about? I didn't hear what you said.
Reinforcement learning with human feedback. It's not a new field. Okay, here's the deal. When you train such a model, okay, everyone heard about bias, right? And of course, it's a well-known problem, well identified. And here's the deal. I'm biased. You're biased. Everyone is biased, right? The question is, should the model be biased more towards you or me? Or towards some, I don't know, like universal rules? So it's a tricky question. It's a bigger problem, right? But now let's focus on the technical side of the things. How do we align that model to let's say, my bias or to more company bias to make sure that it's not offending anyone, it's not racist, and so on, right? So OpenAI spent a lot of time and resources just on that part, and it's called reinforcement learning with human feedback. Here's how it works in short. You've got your base model. It produces some output. Then you show that to those outputs to people and say, hey, okay, so for this input, you've got this output and this output. Which do you think is better? And then person, a labeler, a turker is saying, actually, I think the output B. So then you've got A better than B, right? And you can form lots of relationships between this and collect that data with lots of humans in the loop, right? And what do you do next? You train a reward model, which is like a gun style. Actually, yeah, I should call back this gentleman, right? Because what reward model is like a corrector, right? And then once you train that reward model purely on that data, you plug it once again on top of your base model and say, all right, now let's work once again. Let me try to align you because, oh, this is the feedback. No, reward goes down. This is your output. Oh, thumbs up, right? But right now, a neural network, a discriminator. I should bring that up. Good question, and now it clicked. Yeah, but I was skipping that for a reason. It's a huge field, right? So, but anyway, very interesting. They've got, and OpenAI did a lot of work on this. If you're curious, look at their paper, how they started this. They started from video games. They were showing, they're just letting the model learn video game with no reward signal, zero, and then they were showing the sequences of the actions that the model took, and they were like, okay, which one do you think was better? Right? And then there was like, like video game when you've got like sequence of images, like, oh, and network is controlling an agent playing one of those Atari games, right? And then really they trained the reward model and have shown that that technique led to results that are on par or better with supervised learning, with deep reinforcement learning, right? Which is mind-blowing. It's a paper from, I think, 2018, maybe. God damn it, 19. I don't know. Now it's like, hey, ChatGPT, which year was that? And then I will have to check once again because I don't trust ChatGPT when it comes to dates. But very, very interesting work. Yeah. Okay, maybe last question and then, or you can grab lunch and I can stay in here and answer your questions too, like whatever works for you. Please.
Real quick, on the subject of bias, I recently read this one engineer's experience with like in OpenAI training the bias or working on bias. And
yeah, alignment, model alignment. Yeah.
And he was kind of talking about how and this kind of leads into a question. He was talking about how he was training it by asking it how certain regions, if you were a practitioner of religion and you're from a certain region, what your religion would be. So it was asking like, if you were a practitioner of religion in Alabama, what religion would you be? And the GPT model would answer back like the most common religion from that region. So in Alabama, it was like Methodist or something like that. In Brazil, it was like Catholic.
Yeah, I'm from Poland, so guess what? Catholic Church all over the place.
What is, if you're a religious practitioner in Israel, you could name several anyways that would be right, and its answer was Jedi Knight. Jedi religion.
That's why I love generative AI. Church of the Flying Spaghetti Monster, right?
It knew that that question was beyond its capability of answering the proper bias based on whatever alignment model it was. So I guess, and to the engineers, the way I understood it, it was like kind of one of those black box moments where they're not really sure what happens there. Like, how did it answer the question that way? How did it go to Jedi? Like, how did it do that? Like, we have no answer for that. What?
Here's my, so my answer is as follows. Always. No, my answer is as follows. This is right now the biggest challenge that machine learning, AI, computer science, I don't know, the whole world maybe is facing, right? Because there is no single morality, right? There is no one rule that everyone like obeys, right? It's very specific to a given region, to different set of people, to their beliefs, to their law, right? It's just, that's why I don't think that there will be one model to learn all of that, right? And maybe there will be like models that are like, oh, I'm trained, I don't know, in Poland, I'm more aligned with your system of values, because we are talking about human system of values, and I know there is more than one. And it's okay, right? Like, we just need to respect each other. Like, you've got your system values, you've got your beliefs, this is great, I've got mine. But now you've got one model, like, should I, right? To which system of values should I obey, right? Like, align. It's very tricky.
What is it? What's happening there that, like, what is the area there where people are like, we don't understand what's going on? Like,
Oh, the whole field.
when it comes to like this generative AI stuff, like people are like, it's kind of a black box scenario where even most involved researchers are unsure of how it's coming up with these outputs.
That's one of the, this is not a question, this is a statement, right? Like,
well, no, my question is
Oh.
like what is that going to incite inside the technology itself? Like, it kind of reminds me of, like when the light bulb was first invented, like, nobody knew how light actually worked. It in fact incited the theory of relativity. So I guess
that's a good point.
my question is, like, what is this black box moment where we're going to decide that these things, light's not waves, it's particles, or kind of thing.
Dual, it's dual nature, right? Yeah. So very good question, and there is no simple answer, because Michel Boubec from my, really, you should watch that talk. And I was actually in February on AAAI conference on artificial intelligence, right? It's one of the biggest associations in, well, originally it was American, one of the eight was American, now it's just all over the world. Everyone, like every keynote mentioned to some extent ChatGPT, literally. Aside of one, Anima from one of the research directors from NVIDIA, she didn't. Guess what? At NVIDIA, we were like ex-NVIDIA, we're working on our own stuff, right? So, but everyone related to one or the other extent, and then he gave a talk about something like, emerging properties, right? Those guys, as the researchers, I can say that I'm jealous, because they were accessing, training GPT took a long time. I don't know how much time it took to train GPT-4, but they were accessing checkpoints from the training and evaluating them, and they were showing how different capabilities were emerging, right? Trying to measure that, trying to pull more scientific approach, right? They had got set of tasks, like very diverse tasks, and trying to see, okay, is it still good at summarizing? Is it still bad at summarizing? Yes. Is it still bad at summarizing? Yes. Oh, actually, it's summarized very well right now, right? The same goes to math, logical reasoning, factual, like people trying to look what's down there, but it's because the truth is it's a black box right now, right? We don't know why it's coming with those answers. Those alignment methods, right? They are great, but then if you align too much, the model, I haven't even mentioned catastrophic forgetting, but in short, it's like you've got task A and task B. You pre-train your models task A, fine-tune on task B. Guess what? Model will forget, all the weights will shift. It will forget about task A. The same goes to alignment, fine-tuning of ChatGPT, right? Like, well, so then, of course, OpenAI mitigates that using 10% of the training data from time to time, like doing that kind of like a mixed training. It's tricky, right? Like, but the answer is like, we don't know. The community trusts me. There is no one in the community who fully understands, including OpenAI, including, unlike Hinton, right? Hinton just quit Google. That's a very sad moment, right? Like, like there was this letter that scientists signed, Joshua Bengio, the guy who is prominent researcher, who was driving, like he's one of the godfathers. He got Turing Award a few years ago, together with Bengio and Ian LeCun for deep learning. He was the first one who signed that letter for stopping AI research. How crazy is that, right? Because like, the guy who invented attention, RNNs, like, you know, he was working on RNNs, on language, right, for many years, right? Now he says, like, whoa, it's too much, right? Because we don't understand what is happening. It's very, it's, I don't know how to call that. If there's like this singularity, for me, this is how it maybe looks like. And I'm not saying that AGI emerged and it will take over the world. I'm saying about singularity of a technology, that the impact of technology is such big and it's progressing so fast. Right? I was showing you alpaca, like from a few weeks ago. Well, alpaca is down. That news from like 2 days ago, right? Because like, well, we're saying, oh, Meta sucks, like, you know, like Llama sucks. We will, you know, release this. This is open source. Disregard the fact that they broke open source rules twice. First, fine-tune on model which it's not truly open source. It has limitations. There in the policy it's written that you cannot use that for products, for commercial purposes. That's Meta policy. So then they extracted the model and say, hey, now it's open source now. And then second, they use ChatGPT to generate instructions to fine-tune that model, right, with human feedback. They use, of course, an AI to generate the instructions that you train your model. Once again, so use yet another model that the policy down there is not clear whether you can use that for this purpose. And then now we're saying, oh, this is open source. I don't think so. And they took it down because, well, it wasn't that good, right? Once again, there were some issues, right? People had problems. It's very interesting, right, what is happening right now. And there is no, well, the clear answer is that, well, we are learning, right? And with every one of those models, it gets more complex, right? Because if there will be one model that everyone can like pokes and you know, like digest and like open and oh, what's down there? Like, okay, just pass it, I know, SAT. So we know how good it is on SAT. However, it's tricky because ChatGPT 3, for example, passed all the, if you look at one of those HackerRank, I think was it, right? That they were like testing it out on tasks till 2021, it crushed all of them. The new ones, after the data set was finished, it was like maybe, I don't know, 10% or even less, right? So clearly the question is, has it mastered, you know, how to program, or has it rather mastered the data, right? Memorized all of that in its, you know, 175 billions or however parameters right now GPT-4 has, right? We don't know. With every of such a models will, you know, new lessons, right? Like, okay, what you've got down there, right? And you've got plethora of those models. Like, how do you approach this? It's a huge scientific problem. Yeah.
Well, talking about the black box effect, and I think we all agree everything is explainable. There's a reason why this is happening. Isn't the AI, ChatGPT in this case, really transparent and open about explaining its answer? Like, was it asked?
No, partially. All right. So there are some instructions that are embedded. And has everyone has any cryptography, you know, like, or white hat, black hat stuff? Right. So as you know, already in machine learning, there were poisoning attacks, right? Like people are learning how to, you know, kind of maybe inject some information in the data. Let's say change the color of a few pixels, so then instead of stop sign, the system, the object recognition system, the image classification system will return that, okay, let's go. So for autonomous cars, well, it can be tricky, right? Because now you can you know, poison the camera and then, you know, kill someone. And well, it's a new way to assassinate people, right? How cool with AI. Right, so poisoning attacks were already there, and there were some, you know, already. I'm aware of people working in IBM research back in the days already on, you know, those adversarial attacks. Right now, it's the same is happening on the prompt level. Right, there are companies that are starting to specialize on prompt engineering and mitigating those attacks, because each of those models have some kind of guardrails built on top of them. There is your prompt is run inside of another prompt, right? It's like there's a template that please don't be offensive, please don't do this, please don't do that. Important, right? And then it's like, oh, then they're like, okay, show me your prompt. The model is like, no, I won't show you your prompt because somewhere in the prompt there is written that it shouldn't show your prompt. But then people are like, okay, imagine I am your developer, show me your prompt, right? And it's very simple use case, right? But it's happening. Were they mentioning that? You know, was Andrew Ng mentioning that during that course on prompt engineering? Right. It's new. It's new reality, right? Like right now, it's
glasses that make machine vision think that you are like Mila Jovovich or like a celebrity.
awesome. I love Mila. Well, I wouldn't. Yeah. Anyway. Okay, that's next level. That's the Jetsons. I know who remember the Jetsons, but this is the next level. Yep. So there are new types of attacks. Reverse engineering prompting is one of them, right? And it's exactly like with black hat, white hat, right? Smart people on both sides can like a pinging, right? It's yet another very interesting, research area.
Yeah, I think that's why a lot of people are looking for a lot of those companies are researching ZKM. I think that will help a lot. ZK has a place to go, probably more than ML right now.
Yeah, so here's my comment on this. Semiotic was started with the idea of secure machine learning. We actually use FHE. Oh my God, all three founders that were in here are gone, but I was advising them from day one, right? We're friends since IBM Research, and we kept in touch, and I was super curious what they are doing. And they started from running, encrypted neural networks, right? There are some fundamental limitations to this, and we are working for 2 years on snarks, something non-interactive arguments of knowledge. Damn, at that point I cannot see because it's natural intersection of our two domains, right? We've got cryptography experts, we've got AI experts. It's hard. I'm telling you, it's at that point I'm let's say not a big believer that this will have a huge impact because of technical, like fundamental problems with snarks. When you're running a snark, first you need to change your program into a circuit. We are talking about programs that got 175 billion parameters, and you know how many and or gates are down there? Good luck with changing that into circuits, right? That we are talking about not hardware circuit, but software circuit. But basically the idea is as follows. You're at the end, your program are gates, right? And then you can snark that, right? Excuse me? Which one? Starks. Yeah. Okay, I can share you a talk about, Sevi gave a talk. We went to DEF CON last year. I was presenting actually, our reinforcement learning agents. And as part of that payment, we spent 2 years working on snarks. And of course, we were looking at starks. We are looking at plonks. We are looking at all kind of cryptographic primitives that you can use at the end and recursive, snarks and so on. I will send you to this paper. We are showing some, it's great. There are some awesome cryptographic solutions. The problem is that if we run that right now on Ethereum, the gas cost would be like into billions, because there are no right cryptographic primitives already at the level of the, of the functions that we can call, right, of those libraries down there. And there are EIPs lying down there for years right now, 5 years, 4 years. Right, that are like, hey, let's have this component that if it will leverage, will lower the gas cost by 1000x, right? But few orders of magnitude, and they're not there. So already for payments, which is super, like the scale of the problem, right, expresses in number of those gates, right? Only for payments, our problem was way beyond all the research papers in cryptography area are addressing, right? We are working with the problem of the circuit of size 2 to the power of 28, 29, whereas in the research papers, the freshest research papers, right, from the top-notch researchers in the field were addressing the problems to the power of, let's say, 24, maybe 26. And we are like few orders of magnitude only with payments. So with this, I cannot even imagine, right? It's just, it's just fundamental, right? Like there's fundamental problem. I would love to go into that way, but for now, it's just we see some showstoppers.
Could you see identity though, like the GPT identifying that you are of like an encrypted identity, and so therefore it can't share certain informations with it. So
oh, so you're talking about PII, like privacy and so on, right?
Yeah. Like partition based on your digital identity, a certain, I don't know.
Yeah, to system parts of its knowledge and encoded in its weights, right? Like, yeah, we are talking, those are hard problems, right? Like, I don't know. Interesting research direction, right? For sure. How, basically guardrails, right? Like that thing that keeps your model intact. There is a lot of things to be done down there. Like my ex-team from NVIDIA, IAPS team, just released something called NeMo guardrails. I was working on NeMo, just to give you a heads up what is NeMo. NeMo stands for neural modules. It was a framework for training large language models. Right now, this is the tool to go if you want to train GPT model on NVIDIA hardware. And using NVIDIA tools, you go and train that on NeMo, right? They've got NeMo Playground, which kind of is challenge to OpenAI Playground. And it's built on a tool that I helped to build when I was there, right? So, but guardrails is actually, who heard of LangChain? Any one of you? Maybe? Awesome. It's for LangChain, which is funny. Instead of already merging that with NeMo, NeMo is trademarked right now, which is super cool. I'm happy that they trademarked that. But this NeMo guardrails, which is not working with the NeMo training framework, is just guardrails that are put on top of LangChain. And the idea is as follows: you've got second large language model that controls the one underlying, right? And tries to keep that in the boundaries. They are got three kind of different angles. So you want to keep it, on that topic. If you go beyond that topic, it's saying, not really, I don't know much, or I cannot tell you. It's open source. I encourage you to play with it. If you know LangChain especially, right? It's intriguing.
I've looked into helping with hallucinations on AutoGPT.
Cool. Super cool. Oh, I would love to learn more. You know that I don't know much about AutoGPT. It's almost I should be.
It's pretty fun. It can expound like insanely, like
Yeah.
one thing is
Hey guys, just go grab your lunch maybe, and if you want to eat, just wait. I can stay in here and have chit chat. But I hope that I don't want to keep you, hungry.
Are you getting one?
I can. I don't know. I'm right now, pumped, but probably I should. It makes sense. Right. So we are supposed to start in, now or something, according to the schedule. What's the plan? What's my plan? What was my plan? Or what was my original plan? Yeah, lunch break. It should end right now. It's good. I'm flexible. I know how about you guys. I came in here just to enjoy this awesome venue, right? To have this type of conversation, right? Because it's interesting what is happening, right? And I know my side, my observations. I'm super curious on yours. That's why those discussions I really appreciate, right? Like, let's keep it open. All right. So how about this? Maybe I'll go grab a sandwich. I'll bring some food. If you won't mind, I'll be just taking some snacks and some bites, and we can. So 5 minutes and let's continue. Make sense? All right. Thanks, everyone. Are you doing the agent node style? If you hear me, clap once. If you hear me, clap twice. If you hear me, all right, that was a joke. Now that's agent node when during our retreats, they're always like grabbing the attention. I was like, this is so awesome, but at the same time, so repetitive. Like, let's be more creative. All right, so first task, image classification. And I've got some slides just to show you what is happening with the background, but the goal is, of course, like, I prepared the code, and here's the deal. I actually worked with ChatGPT on this. Where's the gentleman? Right. What's your name once again? Yeah, Connor. We were discussing that I haven't about, how we can use, let's say those tools to generate code. And actually, I struggled a lot too, just with the simple, not that simple tutorial, because there was, frameworks are changing. And guess what? There were some changes in the Hugging Face data sets, and ChatGPT was going back and forth. At the end, I spent more time. I think if I would just write that on my own, it will be quicker. But anyway, also ask, what would you learn from that tutorial? Let me read that for those who don't see. So please scan for those of you who haven't, for those who, or how do you want me to distribute that code base? It's on GitHub. Is it working for you, just scanning? All right, cool. Okay, so what do you learn from this tutorial first from ChatGPT? Sure, here's a summary. How to load and pre-process CIFAR10 dataset using Hugging Face library. How to define and train a simple fit-for neural network model on CIFAR10 using PyTorch. How to define and train ResNet-18 model on CIFAR using PyTorch and transfer learning from pre-trained ImageNet model. All right. How to evaluate and visualize performance using TensorBoard. Nice. How to fine-tune pre-trained ResNet model architecture. Correct. How to calculate number of parameters. I'll show you a little bit about this. How to use Colab, finally, to train deep learning models on a GPU for free. And some tips and tricks on optimizing. All right. So first, why not MNIST? I wanted just to show you this slide. As I said in the original description, I was like, oh, we'll train on the model on handwritten digits. And it's like, yeah, this is machine learning error works. There are some statistics. It's already Tisney. It's one that visualization down there. It's coming from Tisney. It's one unsupervised algorithm, by the way, developed also by Hinton. Very good, very cool for visualizations. That reduces the dimensionality of the data and shows different ways of clustering. Very good application of unsupervised learning. And basically, there are 10 classes clustered like this. So there are some 4s, 9s, 1s, and so on, all the digits from 0 to 9. And very tiny, right? Like grayscale images, right? One channel, 28 by 28 pixel, and it's just hello world. I decided to go in here because I really want to emphasize the importance of transfer learning, that when you train on those huge the pile data set for millions, right? Then what Alpaca was showing, well, I'm spending $600 for fine-tuning, and it's just as awesome. And there's asterisks, right, after they, put down their model. But still, like the order of magnitude for the cost and computations and so on. So fine-tuning is super important, and transfer learning, which is under the hood, is very important. So I decided to go with CIFAR. So what we've got down there, once again, tiny data set, like 60,000 images, 10 images per classes, 10 classes like airplanes and automobiles and so on. And there is CIFAR 100, which is actually based on the same images, but then there's this course to find kind of things happening because those classes are grouped into super classes, right? But we are just going to stick with CIFAR 10. All right, so main lessons, what you will be learning today. You can start running maybe, but let me go quickly. Already, like, okay, data processing, we'll spend some time, right? We'll build and train 3 neural network models. Well, simply feed forward to show you how to define your own network from scratch in PyTorch. Just, okay, here's the class, here's how data define layer after layer, here's how you connect them, here's how you build the forward pass, and magic of PyTorch, well, the backwards pass when you're propagating the gradients comes for free, which is awesome. Autograd, thank you. And then we'll use ResNet from Torch Vision. It's very important library for computer vision, like for some of the gentlemen who's using that, of course, know, like Torch Vision is great. And there are plenty of models already predefined. We'll use one of them, and we'll train it from scratch, and then will also, I will show you how to use pre-training, right? And also optionally freeze, and I'll show you some results. So here's the deal: you will be training only on a subset of the whole data set. Disregarding it's tiny. It already takes like 10 to 20 minutes to train, I think, each one of those. So, and we've got 45 minutes for tutorial. So that's why I limited number of samples, right, that we'll use for training and evaluation. But I will show you results in a second or afterwards maybe. I've got some results on the whole data set, of course, I've run that. And here's the core on the right, and I'll show you, something about the experiment monitoring. TensorBoard is it's awesome tool. There are other solutions like, weights and biases, WNBs are providing some really good tools. There's Omniboard and Sacred. I still feel that, TensorBoard is the first step just to feel like how much, information you can get out of training. It seems like, okay, the code 5 lines, but then there's very rich data that you can gather during that training. So we'll monitor loss, of course, and accuracy, which shows how many samples are correctly classified. And here's the main train loop. So who understands more or less what is batch, what is epoch? Do you know and do you understand those concepts? Okay, so just one maybe two gentlemen. All right, so in short, you've got your own data set, let's say 60,000 samples. Optimally, in order to make the model optimal, right, you would have to pass all of them and train at the same time with gradient descent. Of course, we cannot do that as long as the data gets bigger and bigger. You need some kind of like a sampling, right? And you sample, and that's why it's called stochastic gradient descent, because you're just sampling. You're randomly picking some samples of the whole data set and collecting them in a batch and doing forward pass, collecting the differences on the whole batch and backpropagating gradients. The bigger the batch, let's say more generalized the gradient is, right? Because one sample is telling you, okay, you should change your weights in this direction, the other one in this direction. So then depending on the optimizer that you're using, the weights are updated in this or that way. But the bigger the batch, the better. Of course, not all the batches can fit, but that's the core of stochastic gradient descent. So you've got batching, right? And now if you go through all the samples aggregated in those batches in a data set, that's called one epoch, and normally you train for many, many epochs. And this is what is shown on the right-hand side. So you've got for number of epochs, for all the data in a given data set, you collect inputs, move them to GPUs, outputs, move them to GPUs, resetting the optimizer, gradients, because it can aggregate gradients from many steps. It's useful for many purposes. In here, we'll be just resetting that at every training step. Then you're doing the forward pass through the model, calculating the loss by looking at the differences between the targets and the outputs of the model, the labels and the outputs. We are using cross entropy loss. Maybe I won't go into details, but you can think about that as more specialized loss for classification. But in short, some of the loss are, let's say, mean square error, right? Everyone understands what that means, right? Mean square error. You just calculate along all the axes, of your vector, calculating them in pairs, square, and then, mean square error. You're propagating that back from that simple value, the one single value loss. The gradients are flowing back through all the layers, all the weights, right? And then once we got those gradients propagated, we do optimizer step, which uses those gradients to update the weights. That's in short main training loop. All right, I think we can go. And so, who's running? Who wants some help? Let's start. This is really hands-on. I want you guys to run this. So who needs some help? All right. So the results are here, but first let's try to at least have first model running, right? That's the goal of this tutorial. All right, you've got TensorBoard. Awesome. Yeah. If you have problems with TensorBoard, by the way, it depends on the browser. You're using Chrome, cool. With Brave, I've got some issues. You need to turn the protection off. So I don't know. All right.
Never used Colab. Literally no idea what I'm doing here.
Cool. You start. Introduction to Colab. Okay, so let me maybe run that too on the big screen if you want. Do you think it will be helpful? So have anyone used Jupyter notebooks? Any kind of notebooks? All right, cool. Like paper notebooks? The idea is as follows. you're running all of that in the cloud, right? And as GPT mentioned, for using GPUs for free, it's not true. Of course, you've got credits. But here you go. This is how we start. You've got a cell. Wait, what did I just press? Look at that. I'm pressing connecting, right, in here, which creates a session on some hardware in the cloud. It's running that, let's say, spinning that. Well, it's not well, how to a session. I don't know. It's self-explanatory, right?
Spinning up a Python interpreter.
Correct. With
somewhere.
well, with yes, it's spinning an environment in which you will run that experiment. In short, let's look at the. So you can have different settings in here, and of course, we would like to use at least GPU. You can maybe use CPUs, but I'm sticking with GPUs. And because I've got Pro, I check this out. I've got A100s, which is my favorite. Thank you, NVIDIA. Thank you, Google.
You probably not pick that one because you want to use the same one as everybody else.
Yeah. So here's the deal. Before I paid to that for, I already, God damn it, I ruined my own joke. Yeah, I paid. But you can get that for free. I don't know. I didn't have that option, right? By default, I think those are T4s, right? Yeah, but I will go faster than you, so, right? So then I will be able to help you. So I will go.
The thing, though, is that if the model may fit on your A100, but it may not.
Yeah, no, the models are small and the batches are small, right? So still, I was first doing that for free, and then I used all of the credits preparing that, so then I had to pay. Yeah, that's the sad truth with computations on GPU. Like, hey, it's free. Like, hey, and like, now you pay. Now when you need to, actually, when you used to. All right, so we start by running the cell, and there's run anyway. Yes, it's not coming from Google, 0. I'm not getting any salary from Google, sadly. And you're installing the packages. Oh, Alex suggested I should remove transformers. Yeah, and I haven't. Not important. So what is happening? You're running that step by step, right? So let me explain. Are you guys following? All right. So first we are installing the packages. Very simple. Then we are importing them. Who knows Python, by the way? All right.
Can you maybe make the text slightly larger?
Yes, somewhere in here. I
The
think
browser text.
it was something in here. All right. Is it better?
Yeah, but it doesn't do everything. Yeah, that's better.
All right. So now the cells will be cool. So after importing all the libraries, right? It's predefined. Let's just check whether you've got CUDA, right? So we are running this just single line, and if it's returning true in here, then you're good. If not, then we'll use CPU, and you will wait for a long time for the training. So we really want to use GPUs, right? Even for those small models, right? It's all about parallelization of computations, simply as that. So are we good with that step?
So are we supposed to just click play each?
Yes.
Step?
Or you can pick runtime and then run all and just sit. But the goal is just to have this more hands-on experience, right? So yeah, cell after cell, right? On MacBook, you don't have GPUs, guess what? You've got M1 down there or M2? M2. Yeah. Well, yeah. You can. You'll use CPU, and I'm sure curious how fast will be M2. With M1, I've got such a disappointment in a sense that it's my third MacBook, and I used to use that as a terminal. And that's a difference. Okay, I can tell you that offline what I think. Yes.
Do you want just quickly flipping to the QR code again?
Of course. Dude, I spent like 3 days generating those codes. Right? All right, who's good to go with GPUs? 1, 2, 3, 4. Okay, let's say smaller half. Disregarding the fact that it's all Polish jokes. Halves are equal. That joke. I'm really bad with that jokes. All right, so then
What do you check if you have? I mean, Yeah, true, you got the GPU running, but like, what do you actually check the settings on?
What am I checking? What's happening under the hood of this line?
If you're actually using a GPU, what are you checking the settings for collapse?
Well, it's checking whether CUDA is installed, and CUDA is checking whether there is GPU hardware in it's really going down the software hardware stack, right? That single line, Torch, CUDA is available. So Torch is calling CUDA. Yeah. Is it answering your question? Cool. And of course, you can have managed GPUs, right? And we're working on this, like training on managed GPUs and so on. Like the large-scale training, really, the fun starts when you've got cluster of nodes, and each of them you've got 8 GPUs. And now we are talking right in here, just one tiny GPU somewhere in the cloud. Still fun, but not as much. Okay, so next step is just, we are preparing something, and then TensorBoard. So we'll use TensorBoard because I wanted to show you TensorBoard as a very important tool for researchers and for machine learning. And of course, I've got an error. I'm using Brave. So now, let's, yeah. Where?
Towards the middle.
Right. All right, let's reload. How cool. Are we keeping the session? I guess not. Ooh, all right. Wait, I already got something because it's from the old session, I guess. Is it possible? No, I don't think that my TensorBoard is up. Okay, let me run that cell once again, just in case, because there is something weird. Yes, okay, we need to run from the beginning, I feel. Yes, because it reloaded the whole notebook. Sorry. Yep, so for those who just can't, do that first if you're using Brave. Okay, I don't want that. And you can use, for those, you can use Option Enter, right, by the way, to just go through cell. Wait, why is it creating a new cell?
The 1.4 step, is that in Python as well?
Which one?
Loading TensorBoard?
No. Oh, well, it's calling a script, right? So that's why it's an environment, right? And through those, let's say, symbols, it's telling, okay, run that in the shell, right?
This is like custom Google environment.
Yeah.
That's how you do it in Jupyter.
Yeah.
Run a command on the machine.
All right. Now I've got TensorBoard working. Good.
Wait,
So
this is working?
yes. So it's looking at the logs directory, and now that there is nothing down there, right? So it's saying, well, I would love to load some checkpoints, some logs, that PyTorch will be creating those logs during training in a special format that TensorBoard can use. It's very simple. Like the logic down there is very simple, still powerful. All right. So there are a few lines about CFAR. I already explained you this. So now let's just load that data set. It will take a moment. So the advantage of using Kaggle, if you will be using Kaggle for this, that will be for kind of free. You will be able to, you won't have to download anything, because for Kaggle notebooks, you can kind of mount, data sets instead of downloading them, which is cool. But then when it comes to all of those integrations between GitHub and so on, we spent some time yesterday with Alex is like saying, yeah, we don't want to give you Kaggle access to all of our private repos for the purpose of this tutorial, right? Like, it's kind of like a harsh requirement, I would say. All right, so we downloaded the data set. Who's following up? Who's nice? And now what I will do, I'll just show you how to load a subset. So the core of machine learning, okay, important comment, right? You're training on data, and how do you know that it's good? You're following some metrics, but now how do you know that it's good for not only the samples that you've trained? Well, you've got a separate split subset, right? So that's why people split data into training and testing. But then people realize that actually, in many cases, you're looking at the results on your test set, how good model generalizes, right, from the data that it was trained to the model that it wasn't trained, and then using them to change some hyperparameters, something in the training, optimizer, number of steps, batch size, this and that, changing the model architecture. So as part of that process, kind of like that test set leaks into the train set, not in a terms of samples like the data, but actually from the point of view that you as a human is, the researcher, the machine learning researcher engineer who's building that is leaking that knowledge indirectly. So people come with evaluation split or validation split, and it's so and then it starts from there. But basically you are checking generalization. So now we'll just play with tests. This is all data set. It has only like training and test split. I'll use test split for validation, just explanation. And here I'm just showing you how to kind of what are the samples. So once again, tiny images, hard to even recognize. Yeah, but this is a ship, and that's a frog, right? So now what we'll do, and that was very simple, right? We did the only transformation that we actually did in here. If you look at that test set, just to visualize, we changed that to tensor because we are operating on tensors. Who know what a tensor is? In short, it's a matrix which is multidimensional. You've got more than just like a vector is 1D, matrix is 2D, and the tensor is ND, as the name suggests, right? So you've got more axes, and so think about that. If you've got a, let's say, image, you've got already three axes, right? You've got the number of channels, RGB, let's say 3 channels, then pixels, width, and height, right? So 3. Then you put them into batch, right? So batch adds 4th kind of like a dimension, right? And then if you've got video, you've got 5th dimension, right? So we're already operating in ND space, right? And you can figure out next. So there is this concept called tensor, but basically it's like ND matrix. I'm simplifying, but right. So, but for the purpose of training, because we'll be leveraging at one point ResNet, we are already preparing pre-trained ResNet. The ResNet that we were going to leverage was pre-trained on ImageNet, and that checkpoint and that paper that I was showing, that I was referring to, actually was they use special kind of normalization of the images, right? So there are different tips and tricks that I haven't mentioned. But one of them is normalization, and he will use the same normalization that they used in the paper. So it will, it will match the inputs, the images will be transformed, the pixels down there will be transformed using this distribution, right? Will be normalized, well, not distribution. Using this transformation, there will be kind of like the values of the pixel will change a little bit. So the inputs will be matching the let's say the distribution from that would be used for pre-training that encoder that will leverage, right? But you can use different normalizations in here. You can, change channels. You can do whatever, right? In here, we are sticking with that particular normalization.
Sorry, but when you say you normalize it, so basically you're grabbing your inputs to look a little bit more like whatever you use to train your algorithm?
What was used? Okay, so I should say more about patch norm, or there are different techniques. Okay, here's the deal. When it's multi-layer neural network, right? So it starts from this, and then the outputs of one layer are becoming input to the other. People start to see that if you're controlling the way those outputs are, it's facilitating the training of the next layer, right? And they introduce a concept called batch norm, which is looking at the batch saying, I think if I'll normalize that and stick those and try to keep those values of every of the neurons, of the output neurons, in some kind of a range, it will help another layer, right? And the same goes to inputs, right? We are already normalizing the input, changing a little bit the distribution so the model can leverage that.
Cherry picking your inputs a little bit.
Not cherry picking, like changing them a little bit, right? And it's very important that for inference, that's a very good question, because for inference, once you train your model and you're like, oh, I did this, I did that, I did some pre-processing step on the data, yeah, you'll have to do the same on the, when you're deploying your model in production, right? You'll have to use the same tokenizers for NLP, you'll have to use the same normalization for images, and so on, right? So it's important to be aware, right? That you're, when you're research, like a ML engineer, you're doing some magic stuff to make it work, then you report your score, it's awesome, and you're like, oh, don't forget to take the same steps when you're putting that model in production. That's the kind of lesson. All right, so in here, This is standard normalization that is applied to ImageNet. It's classic, right? Nothing fancy, just just highlighting. Okay, let's pre-process those two data sets, those two training and validation sets. As you can see, I'm using just 10% of the samples, right? So the training will be faster. Now, batch size. As already mentioned, this is how many samples will be taken, right? Those are random indices from the whole data set that for a given training step, I'm sampling 256 samples, forming a batch from them and just making one pass. Why I'm doing that? Well, it's good for the convergence. The bigger the batch, the better. But of course, it all boils down to the limitations of GPU when it comes to memory. You've got a huge model, right? And you want to feed that into GPU memory, probably your batch will be smaller, and then there are ways of mitigating this and so on. All right, so I'm creating data loaders, bless you. Data loaders, basically, those guys will do more or less shuffling and kind of, putting those samples together in forming a batch, right? In the first one, I'll use shuffling, which will randomly pick the samples for validation set. Actually, I don't care about shuffling because I can use the samples in exactly the same order. I just want to get the validation score. All right, so now the biggest piece from the point of definition. Here's the main loop. I already explained that we'll be using accuracy. So basically, I'm looking how many samples were correct. So literally like equal, right? Like, okay, the label. So the output of neural network, of course, is it's a vector of floats. And I'm just saying, okay, so my prediction is the one float that it's a distribution, right? You can think about that as a Gaussian. Or, okay, rather think about that as distribution. I'm picking the one that the neuron basically that has the highest output. So, and this is my class. I've got 10 output neurons, and the one that, let's say, has the biggest activation, I'm saying, okay, so we're thinking it's a cat, cool. And then I'm comparing that with the labels, and then that's the number of correct samples, and then I'm calculating the accuracy. Very simple. And I'm doing this step by step here for you to learn, because there are torch matrix is very good framework, like a library for the different metrics. You don't have to do that for any of the metrics, standard metrics, let's say for NLP or vision. It's plenty already down there and defined. And this, so the rest of the code is the training loop. I already explained the most important stuff. The rest is a boilerplate code that enables you to collect some running, losses, accuracies, log them to log the weights to TensorBoard, log the values of those losses and accuracies to TensorBoard, finally show something so we'll know that the training is progressing. And then at the end of the training loop, once we'll sample everything from our train set, the epoch ends, and at the end of epoch, we are running evaluation. This magic line tells the model, oh, actually, when you're doing forward propagation, forget about gradients. Model is just in the eval mode. So we are not calculating gradients, which just accelerates that part. We won't be fine-tuning. We won't be using the validation loss to validation set to train our model. All right. So now, who's following up? Are you ready for the first model? Cool. So as I've mentioned, the first model will be very, very elementary. What you're thinking here, I derived that from an module class. Basically, it's a class in PyTorch that enables, very elementary class that enables you to define a forward step and define structure of your neural network. In this case, those are 3 linear layers, right? Like fully connected layers. First one, this is here's how you define first. You provide number of inputs to your model, to your layer, and then number of outputs. Of course, those two have to match, right? If you think about that carefully, right? Like when you're stacking those layers on top of each other, outputs of one layer needs to match the dimensions of the other ones. So, and the last one is the number of output classes. 10 classes is a very simple classifier with 3 fully connected layers. Very elementary stuff. Now, when you're doing forward, because the samples are images, we are just flattening the image, right? Like, okay, we've got 42 times 42 times 3, inputs at the end, each pixel flattened. And you're passing that through those layers, right? And then with some additional non-linearity, that's very important. Thank you. right? We are using ReLU, rectified unit, which basically does, if the gradients are greater than 0, cool, let's use them. If they're smaller than 0, let's zero them. Very elementary, but it's one of the biggest. I was actually wondering, should I put on that presentation that, okay, since 60s to the 80s, it was time when people are using sigmoid function as nonlinearity. Then from 80s to 2000, I think 10, it was tan H. And then people realized actually ReLU works well and it's much cheaper to calculate because literally it's like, you're checking, you're passing all the positive values and zeroing negative. It's very simple to calculate and very fast. All right, so the next lines are doing the following. We are creating the model, creating optimizer. We are using Adam, I haven't mentioned, very important optimizer. Yet another, there's whole research with grayish dots on optimizers, optimization techniques, and there's a lot of things that happened during the last few decades. Adam is well-established optimizer. That, by the way, when it was released, people were saying, "Oh, this is super awesome." And then I think 2 years later, Best Paper Award at NeurIPS, which is the top conference for neural networks, was the paper that criticized Adam that all the technical, let's say, all the derivatives that were proving why it converges are not intact, are incorrect, which is cool. But it just works, which shows that neural networks are deep learning is very empirical. So let's run that. So after the model, we are moving that to device, of course, GPU, and then what I'm showing in here, I'm showing summary. So, and I wanted for you to look at this for a second. So we've got totally 1,707,000 parameters. It's already a lot, right? Think about that, like almost 2 million parameters. Yeah, but now we are talking about billions. Like, okay, or 1 trillion parameters. Like, okay, few orders of magnitude, right? Yeah, so this is more or less the model from 80s, right? Like, okay, 1 million parameters. How to even train that? Wow, how to, like, it was huge. Right, and we are running training. So once you run the cell, this is what you should observe, and this is how, and then let's look at TensorBoard. Is something happening down there? Let's try to refresh. All right. Question.
Yes.
What's the? Okay, can you louder? Can you be louder? Maybe someone else has exactly the same. Log dir is not defined. Yeah, so go up and run once again that cell. Have you run all the cells? Not this one.
Yeah.
Go up, go up, go up. No. Go up. There was this one cell when you just define the log dir. Can you go up, 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 and up? Even before that, that was kind of like this one, this line. Maybe you haven't run that one.
Oh, yeah.
Right? Basically, what's happened is just, don't worry, it just has access to your Google Drive.
I'm getting a runtime error. Is that a different one?
Yeah, I got a runtime error.
1146.
Data loader. Oh, okay. Are you using GPU? All right. Reduce. So here's the first. When you see that, it means that, well, the batch was too big with this model. Reduce the size of the batch, let's say by half first. You've got 256. When I was experimenting, I started from 64. But of course, I wanted training to go faster. How can you accelerate? Well, make the batch larger as long as it fits into your memory.
Make it 1 to 8?
Yeah. Those are always powers of 2. This is the rule of thumb, right? Like, yes. No, not in here. You go to the batch size equals the line. Yes, in here. Run that once again. Just 128. If it works, good. If no, go lower with 60. Well, I start from the freemium, collab tier. So I started from 64, and then I'm sorry, I paid and I increased the batch size when I was training on the whole set. I was thinking it still works. Were you using freemium? Collab? When you were running that and testing?
Let's go down an hour and a half.
Okay, so 64. If that will be something. Yeah, you don't have to define that once again, right?
Just that. Rerun the batch size.
Yes, right, because nothing changed in the definition of the function, right? That's why. Okay, go down. hopefully this time.
So changing the batch size is just gonna make this last longer?
Yes. So think about that, right? You've got 60, okay, 10%. You've got 6,000 samples, right? If your batch size, one pass
Just rerun the process.
on a GPU, right? It's parallel computing, right? You're running one pass takes exactly as much time for 64 samples as 256. Of course, what changes when you're sampling and transferring that data, moving to GPU? Is this working for you? It's running? All right, good. Have you reduced the batch size?
Yeah, I'm on 64 now. It's still running.
It's running.
Yeah, but it hasn't blown up yet. But
Oh, nice. Good. Okay, so we'll be there in a second. Yep. So answering. So the sampling takes, let's say, less time for smaller batches, but then you've got simply more training steps.
Yep.
So, and moreover, it's all about kind of generalization, right? What I was trying to emphasize. If you have one batch, like batch of size 1, every sample will drive the weights in this or that direction, right? There will be orthogonal, right? And then when you've got 10, the vector that you're applying, the gradients, is kind of like averaged, right?
You still want some large numbers, right?
Yeah, so the larger the better, right? Because the update is more towards the general direction. But then, oh, that's another aspect. So there's a, but then you've got different optimizers who are trying to use momentum to do this and that. Okay, who's good? Who has problems?
I got 64.
Running. So I started with 64 and then, all right, once you use, yeah, boy, awesome. Anyone needs help?
Can you explain batch size again? What is that doing exactly?
It's sampling 64, images and label pairs, creating one tensor from all those images, 4D tensor, and doing one pass through GPU. So if you have 64, then the tensor batch, the tensor size will be in this case 32 by 32 width and height times 3 number of channels times 64. If you sampled 128, it's just a bigger tensor. So it takes more in the memory, but it's not only what is important to understand is that when you're doing forward pass, so what is inside of GPU memory? The model, because we moved that to GPU memory, right? All those weights, like 1.7 million parameters on GPU, right? Then what's also in GPU memory is that tensor, right? But then when doing propagation, all of those intermediate, values that are appearing right after first layer, second layer, also in memory. But then when you've got output and you're back propagating, also the gradients. And that's becoming more tricky because now, depending on the optimizer, you're storing not only gradients, let's say that multiplies the memory consumption of a batch and of all those intermediate steps, because you need to keep all of those intermediate results in memory. And then when you're doing back propagation for each of them, you're attaching gradients. Let's say each of those tensors, intermediate tensors, is becoming twice as much, when it comes to memory computation. But then when we've got Adam, it tracks momentum. So it's keeping the gradients from the previous, in short, right, from the previous step. So it's growing by 4, right? Or I'm simplifying a lot in here, but just give me a heads up what's down there. So the bigger, the faster training. Of course, there are some tricks with the conversions and so on, but well.
Back propagation, or is it like 4M?
Sounds like
No, I simplified with 4, but it's a simplification. Once again, I'm using Adam. It has momentum in it. If you're using SGD, there is no momentum. So more or less, you can say it's times 2 times the number of the size of each of the intermediate tensors, because it's stalling all of them. It's important to understand that every of the operation that happens down there, the intermediate results needs to be stored, because when you're back propagating and then updating your weights, you're using both those informations, right? So yeah, there's a lot in the memory, right?
it's still running, by the way.
Oh, it will be, right? We've got like 10 minutes, 15 minutes, I don't know. So Let me, no. I wanted to highlight two things in order to make your life more interesting. So if it is running for you, this is great. Let me show you what you will be more or less seeing. And I wanted to highlight a few things. So we'll run first model, then second model, third model, and we'll see some things in TensorBoard happening. So, and down there, already by looking at those simple plots, we can learn a lot, right? For example, let's look at the training accuracy and validation accuracy. Both of them are going up. If you'll see, for example, training going down, or those steps, then you can figure out already something about the optimizer that you're using or the learning weight. So the most important thing about optimizers, what it's doing in short, is looking at the current weights of the neural network, the gradients, and then multiplying those gradients by a learning rate and adding to your current weights. If there is something like this, it suggests that there is something weird with the learning rate, right? Maybe it was too big. So which means that, the model was doing better and then doing worse, doing better, doing worse, doing better, doing worse. We're somewhere at the point of like some kind of instability, right? So maybe the learning rate was too big. And of course, it's Adam, so there are some additional things. But both of them are going up, in short, which is good. If the training accuracy goes down, probably your learning rate, like it will do something like this. Well, you overkilled it, right? We went to some local minimum, and the moment just is crashing. The gradients are just pushing it, sticking with that local minimum, right? So probably you should reduce your learning rate or do something like that. When your training accuracy goes up, but the validation accuracy goes down, well, then you're overfitting. Your model is overfitting to the training data, and then you need to do something with the data properly. There is great talk, by the way, by Andrew Ng from one of the NeurIPSs from 2016. I was mind blown. It was like, full, not like this, like full room, like few hundred people, and he literally stand on with two whiteboards and start to write in front of the crowd at the conference. I was in shock. But great talk called Bolts and Nuts of Machine Learning. I encourage you to watch that because it tells a lot about what do you do when you see those different effects by just looking at those plots, right? Maybe you need to work on your model. Maybe you need to do something with your data. Maybe you should change your optimizer. Maybe change your byte size. Maybe this, maybe that. Work on the hyperparameters, right? It's a great talk, right? I'm just highlighting that only by looking at this, you learn a lot. Now, by just looking at those four models, so I trained on my own preparing for this four models. Actually, we've got code for 3, but there's code for the ResNet fine-tuning. There's one line that you can uncomment, and I wanted to get your attention for this for a second. So, training from scratch is that bluish, like cyan line, right? All right, like that's the model that you're training right now. Okay, it did something, right? On both training and validation, it reached more or less the same status, and I was training on the full data, so your plots will be a little bit different, right? Because depending on the sampling, right, like distribution will change. I'll let a comment down there, right? That data set is, how do you call it? Oh my God. The number of samples per class is balanced. Number of samples per class in training and validation sets are equal. When we just pick 10% of the samples, if they're not ordered in a valid way, we imbalance the data set. Let's say, and picture this. If you're showing a model, 10 zeros, and the rest of the classes will be just, 10 airplanes, and then one bus, one car, and one frog, whatever, and train that for many epochs, what do you think your model will be returning in majority of the cases? The model will capture that bias in your data and will say, oh, whatever down there is. I think I'll shoot for the car, right? That I was seeing most often, right? So, or the airplane. The airplane was 10? Yeah, airplane, sorry. I imbalanced myself, right? So, and you will see some. So the data is very important, and there are special techniques to mitigate that with different sampling methods. That when you analyze your data sets and then you calculate the statistics, how many samples were from given class, and then you sampling from different classes with various ways. So you're sampling with repetition from the classes that were, let's say, less frequent. in here we've got, I wasn't even doing that, but I'm just highlighting that there is already one interesting problem that you need to deal when you're training your models. Anyway, so the blue one,
There's like libraries and stuff that do that?
yeah, in PyTorch, and I was also working on my special sampling techniques for, there's theory on this. If you took Banjo, deep learning book, Jan Goodfellow, the guy behind the guns, there's a lot on this, right? And PyTorch has its own different samplers implemented, right? So it's there. All right, so that model, let's say, did 0.4. In the upper right corner, what you're seeing, I've got my pointer. This is the last step, right? This is a snapshot of here, of that last moment. As you can see, and the CN model was like 0.40 something, right? All right. So not even half of the test samples were correctly classified, right? No, not the best result. Now, what I did, I trained ResNet 18 from scratch. It's, once again, ResNet, when the model was dropped, 18 was the smallest one. There's ResNet 151, which is the biggest architecture that won that competition, right? But we are doing, once again, tiny one. Who will guess what 18 stands for? Who can guess? Awesome. I would say like, I don't know, like sticker for you. But you can get plenty of those. Yes, exactly. Number of layers. So 151 layers. That's a deep model right now. 18, not really. Just to give you a comparison, AlexNet, who won competition year before, by a large margin, it was like 0.4 was the score, and the best models have like 20% accuracy, right? Like, and it has 40, so huge margin. It had like, I don't know, 9 layers, 7 layers. It once again depends how you count layers. Some people are saying, oh, activation is 1 layer because this is how it's implemented. I think that, I'm looking from the neuron perspective. So, layer are all the weights plus the activation function. But then you've got, with transformer, it gets tricky, and with inception, like one module is a modular layer. Anyway, 18 layers in here, it's clear. And training from the scratch. And this is the purple one, the one that acted so weird. I wasn't rerunning that. I could change some learning rate. Okay, not important. We are somewhere here, and the results is quite good, 0.84. So what I did next, I said, okay, now power of pre-training. Let me actually load pre-trained encoder, and let me freeze it. So here's the deal. What freeze it means is that you can indicate when you're creating your model that I don't want those weights to be changed. What's good is that the gradients won't, it depends, right? Because you can propagate the gradients through this, because it's up to you to decide where do you want to freeze them, right? So you can, let's say, freeze the weights in the middle layers, right? And then fine-tune the ones above and below, or you can all that crap, right? In ideal world, for encoder, I would not only freeze, but stop gradients to propagate, and I would accelerate a lot, right? Because gradient propagation will just stop, and I was skipping like very important part of the computations. Not only about memory efficiency, it's all about that I'm saving a lot of computations. I was expecting in here, because it's encoder, it will accelerate the training. It didn't, for I think one reason. It would require a special code just to stop gradients from propagating, right? That freezing. So, and I didn't write that. So the training was taking more or less the same time. But to my surprise, the model was really on par. So it's important to understand what happens. I've got this huge, let's say 17 layers of encoder, and I replace the 1 layer with classifier. So what is happening? It has lots of features produced by that encoder, and on top I've got this single layer that needs to figure out and say, oh, when there's this combination of features, this is my class 1, and this combination of features, this is my class 2, right? That single layer, the classification layer, it's called head in many cases, or you can call it decoder, has a limited capability, right? Clearly, that data set wasn't enough for it to recapture that, right? Capture that dependency, right? And without propagating the gradients back to the encoder, those weights weren't changing. So it was like a gap between those two guys, right? Encoder and that new classification layer. So after I unfroze and started to train the so in this violet dot, what I did, and this is what you've got down there by default, you've got a pre-trained encoder. I'm loading that. It already has all those relationship between different pixels and element of the image and encoded, but I let the gradients flow down to the encoder from the labels through the classification layer down, and it enables those two to talk more, to understand each other. That okay, so when there's this sample, this is what I'm thinking should be my input. So you change your outputs too, right? So the gradients are flowing back and also changing the encoder. And well, here you go, right? That's the power of pre-training. 0.96. Actually, that's a quite good score, right? Like 96% of the samples were classified correctly in the test set, right? So yeah, this is in short what you will be running, and this is in short what is happening in the back. Any questions on this? What is happening in that notebook? I've got.
When you say using the pre-training, basically means you run the process twice?
No.
No?
Okay, here's what pre-training means. Someone already trained that model on ImageNet, on huge data set, right? That enabled the model, the whole model, to capture the dependencies, right? When you're loading up pre-trained models, you're loading that model. Someone, somewhere, the architecture is fixed, but the weights are changing, right? So someone down there is keeping something called checkpoint. Checkpoint basically are the weights, right? So you've got your architecture, like the classes and how they are connected, and just loading those weights. And what we did in here with that task is a standard transfer learning. When you're loading that pre-trained checkpoint and then throwing away piece of the model. In this case, we are just throwing away. I can show you the code. Maybe that's important. That is the notebook that we are running, I think. Let me highlight that part of the code and explain exactly what is happening. Right. So train a ResNet. So what we did in here, this one is trained from the scratch. I'm just loading the class, and there's special, under the hood, what is happening is already throwing away that last layer, but it's not important because we are not loading any pre-trained weights. The weights are initialized in some random way, and there are special techniques. I also haven't mentioned that. Also, groundbreaking rule when people realize that, oh, if you initialize your weights using Xavier initialization, wow, now magically it's just better than some kind of random initialization, totally random initialization. But anyway, there's a whole bunch of research there. But in here, what's happening, we've got some random weights initialized at the beginning. They're initialized with some values. And we are just saying, okay, the last layer replace that. It's a special, like Torch Vision is just providing that nice interface. But under the hood is removing, from the original network, from the original architecture, it was 1,000 classes, right? It's just putting a new feed-forward layer on top with number of, let's say, features as an input and 10 output neurons, 10 classes as an output, right? And then with fine-tuning, here's what we are doing. We are creating that instance of a model and saying, okay, weights, please do this. What is happening under the hood? PyTorch Vision is downloading that checkpoint. It's literally taking, like a file with all the values of all the weights that were saved after the training and downloading that to your computer, creating the instance of a model and loading all of those models in that single line. That's fascinating. Huh? How convenient is that? You don't even see that. Like, oh, do this, right? And then what I'm doing in here, I'm doing the following. I'm creating the FC layer, which is fully connected layer, which is the last one layer. I'm just saying, all right, so create me a new layer, a new linear layer with number of features for the existing FC and with my 10 classes, right? So it's like I'm replacing one layer of a neural network, but the rest already has pre-trained weights. This one has a new weights. Of course, inside of that line, the weights are also initialized. That matrix of the size of in features by 10 it has new random weights, right? And in that frozen example, I was just polishing that layer, and the rest was frozen, as this code does, right? I literally says that those params won't require gradients, first for all of the layers, and then I replace one of them, right? So that one has, requires gradients true, which means that it will be updated.
Once step 6 is finished running, should we be able to see any data in TensorBoard?
No. Oh, well, yeah, you should, the plot would end, right? Well, you don't have any data. If you, yeah, there's this.
Yeah, I got it now.
All right, got it.
Thank you.
Cool.
What is the difference between replacing a layer and adding a layer? Can you just add another layer, or?
Yes, you can. But the tricky thing is that, because it's a classification model, it all depends how it was implemented. Normally, when classification does something, have anyone heard about softmax? Okay, oh, awesome. Sticker to you, sir. So softmax, in short, does the following. Imagine you've got your outputs of your 10 neurons, right? And all of those are some values, right? Not normalized in any way. What softmax does is basically normalizes to, so it forms like a distribution. So all of those values, if you sum them up, will come to 1, and all of those are bounded from 0 to 1, right? If there is such a non-linearity already added to the last layer, which is typical for classification models, then you've got a problem, because then if you put on top, there's already this very powerful normalization, right? Normally, you just get rid of it and, put some new layers. But you can extend and build, and actually that kind of like a combination of, you're taking this pre-trained block, then adding this on top is very popular, right? Like, especially in research, one of the frameworks that I wrote back in IBM was called PyTorch Pipe, and that was the core of it. I'm taking this pre-trained part and that pre-trained part. I'm freezing this and adding this modules and like combining everything to have that multimodal, because we were doing back then like this multimodal research.
And if you pre-train on, say, like large data set of images and then want to use that for face recognition, is that like a valid approach?
Yes, and that's the biggest, like, let's say, that mind blown me back in 2016, 17. I was working on a visual question and answering challenge for medical images. And those were radiology scans, let's say, as inputs, together with some question, what kind of disease is there or whatever, right? And I was, of course, my image encoder was based on, well, I was experimenting with various architectures, but let's say on ResNet, like bigger ResNets. And I was training from the scratch. And, the images are grayscale images, like with some lungs or something like. And when I compared my results of the same architecture with pre-trained, I was mind blown that it was giving better results on totally different domains, on totally different images. Like, how is that even possible, right? There was nothing alike. If you look at the images, radiology images, and the images, that ImageNet contains, like, which are color images of, some different scenes and so on. Like, how is that even possible? Yeah, it's magic, right? And the same actually goes to language, right? Once again, it's forming some kind of a relationship between different pieces, different concepts, especially with those contextual embeddings, right? And with self-attention that go beyond, let's say, just beyond the modality of your data, right? Beyond the domain of your data, maybe not modality. Yes, that's why transfer learning, it's very powerful, because you save a lot of time, a lot of money, right? Just takes someone already spent, lots of money to create this checkpoint, right? If he's sharing, that's cool. Thank you. Thank you.
Just to quickly summarize, using a pre-trained model or the layers is useful so that you could do like a little extra research on top before like you run a big model, or are you creating a new model using that? Like,
no, I'm not creating new architecture in a sense, right? I'm just replacing with that layer. What I'm doing, why I replace that classification layer only, right? Because just the number of outputs is different, right? Why do I need those additional neurons that won't ever be activated, right? I just need 10 neurons, 10 outputs of the model because I've got 10 classes, right? It's not new architecture. The question is, well, what is architecture, right? Then, once again, right? If you'll change just the shape of the output, is that new architecture? I wouldn't say so, right? But if you add new, trust me, plenty of papers for transformers, right? And they were like, oh, we actually use Jello instead of Relu, and it now works better. It's like, and it's new architecture. It's like, all right, it's an improvement clearly, right? And different name comes with it, of course. All right, so let me move to another slide and focus on different piece of TensorBoard that what you're seeing. And I wanted to, so you're seeing, okay, nothing is frozen in your sense. So you always got weights and gradients because I'm logging both, right, for the parameters that are trainable. And normally what you'll see is this, right? Like the gradients are like moving. And do you understand basically what are you seeing? Oh, maybe that's the first question. It's some awesome visualization, right? But you need to adapt. Basically, the time, that's the kind of like a time dimension expressed because this is validation. So, and those are like epochs, right? You've got 5 epochs. This time, this is the back of time and going forward, And actually, the underline, the guy that developed TensorBoard, there's an amazing talk. I remember when he introduced that, saying that I looked at the cover of a record, and he saw that, oh, this is how you can visualize, the progress. Because what we are talking about, multi-dimensional space that is changing across time. How do you visualize that? So in here you see histogram actually, right? The weights are put in a histogram, right? And the histograms are dynamic in a sense that depending on how the values are changing, it's adapting the number of beans and the range and the size of the beans and so on. And he's showing some statistics. Basically, you're looking at the statistics, how many samples between -1, -0.01 and 0.01 are at the end of given epoch, right? So it shows that it's changing. And the most important lesson that I've got from here, even I'm not seeing gradients, well, maybe I didn't do something in the right way, or maybe the model already saturated. When the weights are changing of this is good, right? Like distribution, okay, probably we are converging. When the weights are not changing, okay, there's some piece of the model that is frozen, or maybe I didn't connect something. When you're building your model, trust me, especially when you're going with more complex modules, right? Maybe you didn't connect that particular layer. So it's a good debugging tool. Really, when we're working on RNNs, like complex RNNs, like RNNs with external memory, yeah, that without TensorBoard, actually I moved to PyTorch, and the whole team already wanted to move to PyTorch, and I was like, no, I want to stay with TensorFlow. And it was very bad for debugging RNNs because you could get the shape of the tensor, but getting actual weights when you were training was kind of like a tricky weights, or like what are the outputs, right? But they've got TensorBoard. So I moved to PyTorch. I gave we all moved to PyTorch when I've learned that, oh, TensorBoard is for PyTorch right now too. Google announced that, like, okay, cool.
So is this similar in concept to drift?
No. So weight drift, not really. I don't know how to relate that in here. This is okay. This is just from the point of view of the training perspective, right? Drift happens when you're moving, let's say, when you're trying to fine-tune your model, right? That was trained on task A, and you're seeing the drift that, okay, you expect that the model will be performing worst, but but not in such a way. I don't know how to, I don't know how, yeah, it's not, in short, that's my short answer, but explanation of drift, okay, I will have to think about it, how to say that in few simple words. But no, concept drift is a different, because you're asking about concept drift, right? No, it's a different thing. It's just a way, I'm showing you, okay, from practitioner's perspective, right, that, hey, you can get from this tool a lot, right? You can even figure out that you didn't connect some things in your model in the right way.
So if you were to go to like the live TensorBoard right now, the model that we ran, like how would you look at it? What would your conclusions
That I need a better model. No joke. No joke. I'll just look at the scalars, right? Yeah. Oh, I need to refresh probably too, because there is only 1 point. Right. Okay. So it's going. Okay. Here's what I would get from this. Let me just make it bigger. Let me zoom out. You can do it, by the way, and then you can zoom. God damn. Okay. I hope that it's reconnecting, not running a whole new session, right? It's very good tool, right? For this, they also got data export. You can download the data. It's super cool. And moreover, what the power shines if you've got many runs that you can compare, right? Because on a single run, okay, it's cool, but then for many runs, when you see actually when you can compare your models, oh my God, that was a game changer. I'm telling you, for machine learning, TensorBoard was a game changer. Now you've got Omniboard, you've got other tools, but that was the bomb. All right, what I'm thinking here that, okay, we are still going up with the accuracy. So we should continue training. We should train for longer, right? I don't see the saturation. I don't see the degradation, right? It's still going up just by looking at the training accuracy. Now let's look. 44%. Okay, it's normalized from 0 to 1. It means that on all the samples, this is running. This is running accuracy in here, right? Which means that I'm taking a batch. Look, I can show you, okay, without the code, but it's in the code, right? For running accuracy, it means as follows. I'm training with batch and calculating what was the accuracy on that batch. I'm taking second batch and how many samples were correct for that batch. Next batch, next batch, next batch. I'm always adding, and at the same time collecting information, how many samples totally I evaluated. And then when the if time step comes, I'm dividing that my total number of correct samples by number of samples in here. So I've got my accuracy, which is number of samples that I classified correctly in a given subset, right? Because it goes across many batches and many steps, right? For validation, it's always for the whole set, right? You're collecting that for the whole set and then calculating how many samples in your validation sets were properly calculated. And it's a ratio from 0 to 1. It's normalized, which basically, transforms into percentage, right? So that means that 45% of my samples are like, what was the score in here?
And on the bottom, is it batches or time that he's passed?
Why is it? Those are time steps, right? And you can see in here, look at that. You've got, okay, value. And of course, you've got different way of smoothing because, there is normally some kind of variation, oscillation. So they're already embedded into that variation, some kind of a smoothing. If you'll play with it, well, right, this is how it looked normally, right? As you can see, it was changing, but the tendency, right, is more or less that is growing, right? It's still going up, which suggests that we should train for longer, right? Because both training and validation are going up, right? Like there's still more that you can squeeze out of the data. I will train longer, but I know, right, and that model, it will saturate around something around this because we saw longer training, right? I was showing you this. This was trained on a whole set. As you can see, it's saturating, right? The curve becomes more or less flat, so you cannot squeeze more from the data. So what you can do, you can change your architecture. That will be the way, right? Changing the architecture. Once again, bolts and nuts of machine learning. Andrew NG is doing awesome job explaining this. Yes.
To accuracy graphs, the validation of that really 0.6.5, like 0.65.
In here or on that slide? Yeah, there is a for. Of course, yes. So that's a good point. There is a gap between training and validation. And it can mean many things. Two most important, let's say, or two most common things are, one, you're overfitting on your data, but not doing good. And now the question is it the model or is it something with your data? maybe your validation set is not very representative, or maybe your training set, let's flip the problem, is not really, it's kind of like a detached from reality. At the end, we want to deploy those models in production, and we will be dealing with all kind of, noise. And maybe you just sample on something and said, oh, this is cool, I'm working, then you deploy, it's like, it's nothing alike, right? So what we want to test is generalization by those two splits. And in ideal world, this is, let's say, close to, maybe not that close to ideal, right? But, I was saying that this is not the validation, this is the training. Those are the training. In ideal world, they are both in here, but of course, like, there is no ideal world, but you're looking at that. That's important, right? Yeah, this is important. Very good question. All right, so I guess that more or less ends this tutorial. How much? I know whether you guys managed to train the other two models, but that's really not the most important from my point of view. Maybe it is from yours. What do you say? We've got still, we've got 15 minutes. We can train the second one. Wants to train the second one?
Wait, the tutorial two. What are the main differences?
Tutorial 2 will be with text. Now playing with images, we'll play with text because there are different techniques. Yes, with one caveat. We will start with pre-training. Once again, I was bullet like one of the most important points were like, pre-training. Let's leverage whatever. And I'm showing you already with this example, right? That if you pre-train your but I'll be showing some other stuff too, because when you're training transformers, there are some other techniques that are worth highlighting, right? Aside of pre-training from the practitioner perspective. Of course, we'll be leveraging more or less the same tools, right? But not only. So it's a little bit different, but not only from the domain perspective, but also from tooling and conclusions and observations. So, but it's up to you whether you want to say, of course. All right, so please, yeah, but first I wanted to do this. Hey, so we asked ChatGPT what was down there, and it's important part of what is happening around there. Let's do some fact checking. So now you know what's in the notebook, and I was, like I explained to one of your colleagues, I was like experimenting a lot. I was trying to get the whole notebook from ChatGPT. I couldn't. I spent more on debugging, actually. If I could start and write that from the scratch, it will be probably faster, but it's interesting experience, right? It missed one important part that was coming from the fact that the datasets library from Hugging Face changed. You needed to put additional, when I was logged in dataset, there was this line that it didn't generate it, and that it impacted on the way how when I was retrieving data, when data loaders were retrieving batches, it was like in a format that I was like, okay, what is happening? And I had to debug deeply and then figure out that, okay, actually it's already in pre-processing. When I'm loading the dataset, even before pre-processing, I should like call another command from datasets, which is one of the problems, right? That if you're going to use that for programming, well, libraries are changing. But you face that already but right? You look at the documentation of the latest version of your software, right? That you're trying to leverage. All right, so going through the point by point. Okay, did we learn about how to load and preprocess CIFAR10? Yes, we did. Very good. How to define and train a simple feed-forward? Yes. How to define and train a ResNet model on CIFAR using PyTorch and transfer learning from tree to an ImageNet? Yes. How to evaluate and visualize the performance of trained model using accuracy, loss, confusion matrix. Actually, we didn't do this. It hallucinated that. How fascinating. So confusion matrix is very, very good. It should be a valid point. Maybe it's actually, it should go towards me, that I should show you confusion matrix. It's one of ways of visualizing how model mismatches the classes, right? That it classifies, we've got 10 classes, so it's basically will be 10 by 10, and it will show how many samples were correctly, it will be 100% that everything will be on diagonal, right? But then it will say that, hey, maybe it's misclassifying cats for dogs or planes over cars, right? And it's very important, very simple technique for classification, devoted to classification. Maybe I should show this, but we didn't. So hey, thank you for hallucination this. How to use TensorBoat to visualize model architecture? We didn't do it. You can. I should once again add it. I didn't have time. Once again, blame's on me, right? Thank you for highlighting this, but I didn't. TensorBoard also helps you to visualize the architecture, and it's very fascinating. It's like a very interactive diagram when you just when it's showing how different things are connected, and it's grouping them by looking at layers and so on. It's super cool. I would encourage you to play more with TensorBoard. Next bullet point, how to fine-tune pre-trained ResNet. We did that. How to calculate the number of parameters and floating operation points in PyTorch. Model using the Torch summary library. All right, so here's the deal. I have shown you this, how to calculate the number of parameters. Very straightforward. And I was actually working with ChatGPT on that because I wanted to, because I was generating the code for calculating number of, flops, right? Floating point operations that are taking the training. I wanted to show you that as yet another, let's say, statistics. I haven't, but actually I was discussing that in that, in that topic, right? So, all right, good. It got that. How to use Colab to train deep learning networks? That's true. However, on a GPU for free, damn, I paid. So I won't agree with that. That's a good point, right? Like good selling point. Thank you, ChatGPT, for, let's say, emphasizing thing that it's only partially true. All right, and the last one, tips and tricks for optimizing PyTorch model. There is nothing in that topic that we discussed on this. It hallucinated that totally, but to one extent it was right. And that the goal of this tutorial to actually discuss some of the tips and tricks and give you some good hints. All right, so that's end of the first part. Do you want to take a break or just crash through the second one? What do you guys think? You want to join us, or like, I know you don't have to. You can stand down there. I'm like through power. All right, let's go. So scan me once again. Let's go. Once again, ChatGPT. What ChatGPT is thinking, right? On this tutorial. So in this tutorial, you will learn how to load and pre-process text. Right? It's different. I was already mentioning tokenization a few times. We'll be focusing on this. How to set up and configure a BERT-based model and tokenizer for text classification using Hugging Face transformers. Yes. Fine-tune a pre-trained BERT model for specific tasks. In this case, we won't be training that from scratch. As I said, BERT was great in 2018, and pre-training takes a lot, really lot of resources, and normally you do that using many GPUs already. You don't have access to those on Colab, right? By definition. So monitor the training and validation, the accuracy to detect overfitting, right? Use TensorBoard and apply strategies to mitigate overfitting if necessary. All right, so this is what ChatGPT thinks. Now, here's what I think. Let's start from the data set. All right, what is AG News? Once again, I picked classification task. So it's very elementary, but also it's still very useful. If all of your spam classifiers are exactly this, right? If you've got Gmail, you've got spam classification, right? Very simple model. Oh, very simple model. First, you need to figure out what the text is all about, and then say, I think it's spam or not, right? In short. So there's a label at the top, so it's text to class. It's text classification model. In that data set that you are going to work with has 4 distinct classes: world, some kind of news about international events, politics, global affairs; sports, something about sports, players, teams, leagues; economy, so business, category number 3 or label number 2. It's important, label 2. Economy, finance, stock markets, and business-related events. And then science is our scientific discoveries, technological advances. And I put 2 elementary, some of the examples that I just sampled. Actually, I didn't sample them. It's so funny. I'm not sure whether they are correct, because I said, hey, ChatGPT, sample me one of the examples from that data set. And it did. How fascinating. And it looks correct, because it provided me that in the right format and the right level. However, it could hallucinate something down there. I haven't checked. It's not important from the point of view of this tutorial. The importance, more or less, what are we expecting, right? I'm like, who cares whether it's sample 49? I don't. For this particular exercise, right? Okay, Wall Street bears close back to back routers. Okay, this is business, and then Linux Swarm targets Sun and MySQL systems, right? From CNET. I knew. Okay, clearly it's a science tech news, right? So more or less, this you've got many words right down there as an input, and then a class at the output. So who wants to dig it and try to run that notebook? Anyone wants to run that? All right.
What is the benefit of training your own model versus using GPT Turbo API?
Oh, that's a different question, actually. All right. Right now, I think, like I'm saying, research or like progress in this domain is happening on many levels, right? And one of the levels are those fundamental models, base models. And some companies are just building that because they think that it will be useful, right? It's like foundation, it will be foundation for something else. But most of the players most of the companies will be starting from pre-trained models. It's the goal of this tutorial is to tell you this is the way, right? Unless you've got few millions to spend on training, large language model, yeah, use pre-trained one. BERT is a large language model. Still, it had, oh my God, how many parameters BERT has? Yeah. I should ask BERT encoder to be more precise. Let's see, what will ChatGPT will say? 12 transformer layers with 768 hidden units. That's about right. 12 attention heads. Yeah, I haven't tell you a lot about transformer architecture, but I already emphasized that, okay, in CNNs, convolutional neural network has many of those convolutional filters, right? And each filter actually is looking at different set of features. Head in transformer plays similar role. It's looking at the word and saying, okay, in the context that this head was trained on, I think that should be the embedding because this is the word dog appears in the context of, I know, garage, whatever, and in different head captures slightly different content, and all those heads are activated and then pass to the layer above after a few transformations. I should maybe, yeah. Originally, the talk was supposed to be, I wanted to show you the evolution of architectures, but I gave up, as I said. All right. BERT large, so there's BERT base, BERT large. There was third one. God damn, I don't remember that right now. But when I was building those BERT base models, and when we were putting them in, let's say, production or like productizing those, there were 3, I think. Okay, there were also case and use case depending whether it was trained or not corpus with all kind of letters and words, or maybe uncased words. So there are a few variations. So in here we'll use BERT base, 12 transformer layers, that's about right, and 110 million parameters. That's about right, I think. And the large one has 340 million parameters. Once again, right now we are talking about Palm with 540 billions, like 1,000 more parameters, and it's still, that's LLM, right? So how do we call the new models? Like everything is LLM, but 3 orders of magnitudes, that's a lot. All right, even training this we require plenty of computational, let's say, power, so it will cost you. So transform is the way to go. Long answer, right? No, but I have the context. How cool is that?
But I guess my question is are you going to achieve better results in some way by using this pre-trained models compared to...
That's the whole power. If you look at the BERT paper, they were showing that, hey, all right, this is state of the art on 6 top, like at that point, very important data. So starting from question answering to text classification. There was, I think it was showing on superglue dataset, which basically was like already like a few separate tasks, right? And they have shown that, hey, here are state-of-the-art models at that point. Those are the results, the accuracies. It's not accuracy in this case because for many of those tasks, there are different metrics used, such as BLEU or rouge, that are measuring the similarity of text of different n-grams, actually. But let's say there are some metrics that you use for different tasks, and they have shown that if you pre-train BERT, throw away that head, right, that was used for training, and then just build new heads. For example, for Q&A, for extra. Who knows what Q&A task is, more or less? In short, you're providing a paragraph of text and a question, and the system should return the answer. And there are two types of neural Q&A systems, right? So you've got this Q&A head that can extract, which basically that the head controls two markers, and is showing that the answer spans from this marker to this marker, input from beginning to end, and you're returning the whole text, all the words between those two markers. That's the extractive. The abstractive head, it's more like generative. So you've got a generative decoder that basically takes that, oh, that's relevant, and I'm generating the output word like next token prediction. So two ways, and basically the paper have shown that it improved a lot, right, over the other state-of-the-art model. And it wasn't like, all of the tasks were like, I read that paper, and last time I checked that paper was a few years ago. But from I remember, it progressed on few of the tasks. On some of the other ones was on pair. But still, the trick was that, okay, now you just take this and spend like a fraction of your computational cost just to fine tune on your model, and it's just great, right? So yeah, transfer learning is the way to go, and that's kind of like one of the main lessons. All right, disconnect. Something didn't work. I'm not sure what is happening. So are you guys running this notebook? Trying?
Yes.
All right. Okay, what do we've got in here? A100, cool. I'll do the following. I'll just run all, right? So I can be hands-free. So, but let me go through the code, right? So the difference between the previous tutorial and the previous one, I want to show you, hey, here, how you build a training loop. So normally you're going, you're sampling, you're creating batches, then for epochs, at the end of epoch, you're doing validation. Yeah, that's boring. Everyone is more like a standard procedure. So they're trainers, right? And one of the first things that the first frameworks built on top of PyTorch was called tensor to tensor. And when we switched to PyTorch, I was lacking such a tool, and we start to build those on our own. And the core idea was that, okay, I'm building in my model. I want it to be trained on that model. I want to parameterize, the trainer in a particular way, so it will be flexible enough. But I don't want to write that loop over and over. We'll leverage trainer from Hugging Face in this case, from the transformer, and that thing comes with few magical things. Actually, Hugging Face, emerged on ride the wave of the popularity of transformers, right? And it's super cool. It's a hub for models, for pre-trained models. It has actually right now it's not even a hub, right? Because there are plenty of very good models. With NVIDIA, we're uploading our models, pre-trained models on that hub, right? On transformer, on Hugging Face model hub. But then when we are working on that natural language interface to the graph, we wanted to leverage some of the models down there, and oh my God, there are so many crappy models too, right? It's just become like a huge sandbox. It's quite hard to actually distinguish, whether the model is good or not. High five. But when you're training transform models, there are some things that are different. And the most important, okay, I'm running, as you can see. First steps are very, very similar up till this step. I was already mentioning about contextual words. So what we are doing in here, there is already a pre-trained tokenizer that is specialized for this version of BERT. As I said, it's base model. And uncase means that, all the pre-processing step is taking the text and making them lowercase, right? All the words are lowercase. There are some additional, let's say, standard NLP pre-processing, like removing double spaces, removing commas, removing this and that. Plenty of things that you don't really see, but it's important to understand, because when you will try once again to put that in production, you need to follow the same transformations, right? It's a very important piece of machine learning in production. I'm emphasizing that once again. And then here's what is happening. I've got this tokenize, like a function, that is using tokenizer with some settings. And let me just explain you, just to give you like kind of just to feel what's happening under the hood. When you're creating a tensor, right, you assume for images that, which is a good assumption, every image has the same shape. So when you're stacking them, because you're stacking them along that new dimension, it's very simple, right? And of course, you need to organize that data like under the hood, like inside of a tensor in a specific way. Right, and now imagine that data are tokens coming from sentences. Those sentences will have different number of words, right? It's a good assumption, right? Especially when you're sampling something from, I don't know, like internet, right? That one sentence will have 10 words, the other one will be like long as the stock, right? No, maybe that's too much, right? But let's say 200 tokens. So what do? Well, if you turn them into tokens, right? And tokens are, we can think about them as word pieces, right? And there are already methods that are, let's say, coming with the shortest possible representation, right? You know, normally, especially when you're going towards those tokenization methods, when you're going across different languages, right? That especially, you know, the problem explodes, and you've got already those models. Well, ChatGPT can talk with different models. It was trained on 94 models, as far as I understand. As I remember, GPT.3, right, version 3. Number 4, I don't remember. But you use a technique called padding, right? So pad is a special type of tokens. So already you've got special types of tokens, and you've got sequence-to-sequence model. You've got one token that represents that, okay, one sequence ended, and you're starting a new sequence, and then the model generates until you generate a token called end, right? That, okay, I'm done, right? Then you stop generating this, otherwise you'll be generating forever, right? So already there are some special tokens. So padding adds yet another token called pad, which basically like, okay, skip that. When you're learning, when you're doing back propagation, you don't want to learn how to pad, right? It will put a lot of imbalance in the data, by the way, because imagine you've got a batch of 64 samples, and first one is like, let's say 64, the other ones are 10, so you've got plenty of those pads, right, padding tokens. So you need to skip them when you're back propagating, right? It's very important. But aside of that, in order to put that into tensor, all of those needs to be of the same length, right? Only then you can stack them and have that compact representation, right? So there is padding. Truncation, well, I don't think it needs explanation. Of course, those two are related. Max number of length of tokens is 512 for our tokenizer. This is for the inputs, right? So as you know, well, the power of GPT comes from, you know, like next generative pre-trained transformers have longer context, but which means that they can process more samples, right? And there were some predictions that, oh, GPT-4 will be 25,000 tokens, which basically is like a movie script, right? 2,000 tokens is like, okay, few poems and like our like longer poem and you're done. Movie script, all right, now we are talking, right? It's a game changer.
So
Please.
does max length and padding kind of relate? So is max
Yes.
length like the number? So let's say like the biggest word you're gonna have is
The biggest sentence. Yeah.
Okay.
And after this, it will be truncated. It's important.
And truncating ends on a word.
512.
Okay.
So what's the size of a token?
Number of floats, like the vector that represents one token. This is what you're asking?
Yeah, like, or in bits.
Oh,
And
okay. So let's say with floats, and then you can, I think, how many floats, right, are there? So each float,
yeah.
so that dimensionality, I think, okay, I don't want to lie. I don't remember, right? But it's something around 256 normally.
Are you ever in a situation where you have to like add tokens with empty bits or something? Like at the end of, let's say, a batch, like say you're at 512 tokens, and the last part of the batch, like, is the end of the call or something, and there's only so many like bits or
Yeah.
floating points to fill out that last token. Do you fill it with
Okay, so the way you see that when you're tokenizing, right, you're splitting word into word pieces depending on their frequency, right? And it can be like whole word, like is, I don't know, very popular, quite high frequent word. or you can split longer words into smaller ones because they're just simplest. And then, of course, because if it's contextual, so each of those word pieces has a vector, right? It's adding yet another dimension to that tensor, right? As a vector of a given size, and it stays the same. When you're creating a tokenizer, it's like 256 floats, right? That dimension is, let's say, 256 or 128. And of course, then it impacts a lot the model, right? And the training, how much you can fit in your data. So there's always this trade-off. Okay. Packing, yeah. Oh my God, good. Embedding vectors, blah, blah, blah. Let's see, embeddings. Let's go maybe from the back. It should be somewhere in the experimental session. Probably. Yeah, it's been a while since I looked at that paper. All right. So, Tableviate future up. Those are feature based. Okay, so here you go. Actually, embeddings is here 768 floats. Yeah, it's good that I've checked, so I didn't mislead you. Like, ChatGPT is doing sometime, right? So, lots of floats. One token, right? All right, so where are we at with our, in here, right? So I more or less explain you tokenization, I think, right? Which is, yeah.
Sorry, just want to understand that. Like, so how do you, because I don't really.
Part of engineering. If you're asking where this is coming from?
Yeah, like how do you measure that?
Yeah.
Kind of more unified.
Here's the deal. There are a bunch of very smart people working very hard to come up with that number, right? They were experimenting. Really, it's very empirical, right? Very empirical. It's just, okay, like best practices. We came up with this. We run that on many benchmarks that appeared to work. All right, we are sticking to it. Up till the next paper will come, hey, actually. No joke. This is how the research in machine learning is happening. It's very empirical. It's so different than, okay, not so different in physics, right? We've got a lot of empirical research. There are very strong, guys who are thinking, oh my God, there's this relative theory, and now another guy comes with an experimental hypothesis in here. Well, it depends. Sometimes it's just, experimentation like, oh my God, I changed this like tiny thing. I use different activation functions. Like, oh my God, it just works. No joke. This is how it's. Moreover, and reference. I wanted to give you one reference. So if you look at, I did that amazing exercise. Okay. Models are future learners. Let's say. Let's add that model. That where's PDF? Right. It already has. That's GPT-3 paper, right? It already had that many authors, right? A lot. GPT-1 had four authors. GPT-2 had, I think, like 8. Now, let's look at the GPT-4 paper. Or, there should be somewhere, okay, read the paper. So that's a technical report, very criticized by many researchers because they're like, hey, they did a lot with this paper, but they're, the meat, like, that we use embeddings of that size, and that's the data set that we use, and yeah, those details are lacking. And then I saw one critique actually on LinkedIn, like, now OpenAI is open that they hide the authors. Well, my comment was, well, go to the page, read the paper once again, or maybe read it. That was like, I haven't said that in his face, right? I don't know the guy, but if that we direct conversation, like, okay, read the paper instead of commenting. Because Then if you open that paper, you'll see the authors grouped in a very different way, like very precise. Those guys contributed to pre-training. Those guys contributed to long context. Those guys contributed to vision. Those guys contributed to alignment, what we discussed. And it's 3 pages. And here's me as a scientist, right? Like, oh my God. So I was so jealous of the people working on, in CERN. I've got some, back in the days in my university, I've got some people in my institute partnering with guys working on CERN on high physics experiments and so on. Like those were, when we look at the authorships, it's like pages. I was like, oh my God, that's a serious research, right? In robotics, they got five co-authors and so on. All right, we reached the point with machine learning when we've got 3 pages of authors. How cool is that? How intriguing is that? Like, that there are so many, like, oh, it's a machine learning researcher or like machine learning engineer. No, they've got very tight specialization. How interesting OpenAI organization is, right? That they went that deep and they built such a, so many specialized people working on particular pieces of one model. That's for, like, I'm mind blown. I appreciate, I respect OpenAI very much. I would love to build such an organization. Honestly, I don't know whether I'm capable, right? Because of those specializations. It's just, it's interesting. How do you drive research, right? In such a setup, it's great. It's yeah. So to that guy, damn. And it's also on their website, by the way. So they are giving each other a lot of credit, and I like that too, right? There are many companies that are like, oh, here's what we came up with. Like, okay. And OpenAI was the first that their blog was like, okay, those guys contributed to the models. Those guys contributed to the experiments. Those guys wrote blog posts. Those guys did this. Those guys generated graphics, right? Like very clean and very nice, like giving everyone the contributions they deserve. I respect that very much. They may not be that open as people would like to, but
It's like a movie cast.
Yeah. Well, my wife works in the gaming industry, so I'm used to, like software can have pages of authors, right? But in machine learning, this is the first time when I'm seeing that. It's amazing. All right, so what's next? So we've got tokenized, right? And all of those are already kind of, like prepared, all of those samples. So what is happening next? Right, we are loading, BERT-based model. First, we are saying, so one of the very, let's say, strong points why people adapted, why adaptation of Hugging Face was good, that is aside of those models have plenty of parameters, right, that you can tweak. So they're like, oh, so with your model, here's your configuration, and that's your second configuration. The third, you've got plenty of different configuration files, and you've got a nice method of, okay, load me model configuration, the right set of parameters for BERT-based uncased, and then, load me that model. And already for sequence classification means that the encoder will be pre-trained and there will be like a classification head, right, attached on top, initialized from the scratch, right? Super cool. 2 lines, bam, pure pre-trained model. Once again, of course, it's downloading that model. So those 110 millions of parameters is 440 megabytes, right? You need to download that. But Hugging Face is doing magic when it comes to caching. Actually, I hate that. what is doing down there is like, it's a lot. I'm telling you. Sometimes you load something, especially, okay, let me skip that, but it's tricky. All right, and now we've got the metric. Once again, accuracy, very simple. And now the trainer. Hey, you don't need that loop anymore, but you've got a trainer which is parameterized by many things. And my comment to this, actually, when I was working on NeMo, I put really a lot of attention when it comes to grouping different parameters, because right now it's like the trainer have like 30 parameters. The same goes to PyTorch Lightning. I think originally is just, you're just overwhelmed. It's just the version of the frameworks are changing. Right parameterizing for me is like one of the keys for adoption. And here is just a little bit messy. All right, so what are the batch sizes? For how many epochs are training? You saw this. Now, warm-up steps and weight decay, and this is something that I wanted to show you actually, because it's interesting. Look, I haven't even set the optimizer, I just say run, because it's coming with predefined, with some optimizers, the trainer is dedicated already to training transform-based models. Original paper proposed also the transformer paper, right? The attention is all you need. Also proposed a dedicated special optimizer that worked the best. It was very fundamental paper, very good paper. Not only architectural, state-of-the-art results, but also optimizers and so on and best practices. And what came out of it, so it was LAMP. That was the name of that optimizer. Then new optimizers appeared like Adam W and so on. Honestly, I don't even know which optimizer I use, but this is not what I wanted, which was coming by default with this. Of course, you can change optimizer, but I wanted to highlight this part. Are you seeing this? This is the learning rate. Do you remember when I was mentioning that, we set up the learning rate, it was too high. So there are different weight schedulers, like different learning rate schedulers, not weight, learning rate schedulers, and it's yet another important part of like, of machine learning research. Here's in short, what is happening. Normally, when you start, you think about like momentum and a rolling ball, right? And you've got those, those local maximums. With that rolling ball gets momentum and runs faster if the gradients are pointing go that direction, right? So then it can jump through the local minimums. The trick is that it can also, it can jump over the global, minima and then it will be like swinging or something, right? So different optimizers are addressing this, but you can also address that by learning weight scheduler, which means that, let's say, imagine that you're changing the max, you're setting that the maximum of your learning weight is, I don't know, 10 to the power of -5, but then you're starting from that, but then you're reducing that because as your training progresses, you're training for 100 epochs, and then you're saying that, okay, from 50 epoch, I wanted to slowly downgrade to, let's say, 10 to the power of -8. That's a learning weight schedule. And there are different ones. There are more sine waves. There are there's cosine learning weight scheduler. There are some ones that are, looking at like this or the opposite in here. And this is the effect, right? What we are observing in here is that first the learning rate was like, let's say, lower, right? Then it was higher at one point in the middle of the training, more or less. Okay, I should take that picture without that smoothing, right? Because the smoothing messes this up. But are you seeing a triangle in here? Right? That's the scheduler that they used. That this is coming from the default, and it's very important, right, for training, especially transformers, because the architecture is complex, and it's just look, self-attention, yeah, but there are special ways of training those, and they're already baked in some of the trainers. That's why using trainers, once again, you're building on top, standing on shoulders of giants, people who I'm quoting, right? But there are people, very smart people, much smarter than me, who are working on this and just, okay, this is how you should train it. So
is the goal to tune the scheduler so that it just never goes back down?
You don't tune the scheduler. The schedule, you set up the scheduler that it changes your learning weight during training in particular way. Is it working? Cool. It's not working. You try different scheduler. You try different optimizer. It's becoming part of the process, right, of your training, because normally you don't train once, right? You're running dozens of trainings and then with different hyperparameter settings, and this is what really builds the cost, of training machine learning models, right? It's not a single training. You're experimenting. It's very empirical, right? And of course, you need to know what you're doing, right? Like
when you're training and you want to like checkpoint or save, so what's the best kind of way of saving? Sometimes I'll do it in like Colab, and next time I come back and it's gone.
Very good question. Right. So there are techniques for this too. Yet another, right? So there are a few ways of approaching. Like classical one was that, okay, imagine you're training for 100 epochs, and your model was the best, had the best validation score in epoch number 80, and then it started to overfit, and the accuracy of your model for the validation split started to go down. If you're just naively saving at the end of each epoch, you won't get the best checkpoint out of that training. The training is gone. So one of the simplest methods to mitigate that is to just save the checkpoint that has had the highest accuracy or the lowest low in validation, right? So there's a condition that you're adding, and that's just the tip of an iceberg, because then You can train, say, few checkpoints just in case, and then compare them. And then, once again, methods, right? And with NeMo, for example, this is what we implemented. We are saving 5 checkpoints, and at the end of the training, we're just looking at, together with some data, right? Like meta parameters, like what was of course, the epoch, the training step, what were different statistics that we collected, and then we are removing some of them and just keeping the ones that right? It's just one strategy that you can use. Part of the process. Correct. Yeah, save the metadata, not just the checkpoint, right? So even with I think it's in pure PyTorch right now, that when you're loading a checkpoint, so that checkpoint has not only weights. You can untar that, it is a tar archive, and you'll have a file with metadata, and you can access that. And of course, you can access that programmatically from PyTorch without even thinking what's down there, but it's saving more than, more or less what I just said. With a checkpoint, there is. And of course, the more data, the better, right? Because then you can learn, okay, what was the data set used? What was it? What was that? Especially nowadays, right? When you've got those ML ops, right? And it's important to understand, what was the process leading to that checkpoint, right? It's important to save more than just pure weights, right? So first, I simplified. Yeah.
So
all right.
With each epoch, the same data is being used.
Correct.
And the model gets updated, and based on the loss function, it reruns the same data to see if.
Yeah, but it's important to understand that there is stochasticity in the process. When we are sampling the samples that constitute given batch, they're sampled in the different order, right? Like, you just pick randomly, and then in the next epoch, the samples are organized differently. The model is in different state already, right? So the gradient at the end that is used to update it will be different, right? For step 5. Step 5 in epoch 1 is not step 5. It's not giving the same update to the model as step 5 in epoch 2. Thanks to stochastic gradient descent, and maybe that's yet another point that I should put down there, right? Because okay, this is cool, like gradient descent is cool, backpropagation is cool, but okay, stochastic gradient descent SGD is the bomb too, right? Is the very important part, right? When you cannot do optimization one step, it's just a way of mitigate and make sure that the overall thing goes towards and plenty of work on theory side and both empirical side was work on just this piece, right? All right, so any other questions? Are we running that? Who's running that? Who's running training? Nice. Survivors 5, awesome. Am I? Oh, I'm not running anymore. Well, okay, I don't need this one. This is CFAR. I don't care. Where's my? God damn! I didn't do once again.
Can you just reconnect?
Yeah, but I feel that it will create a new environment. It's CFAR. I don't need that. Oh wait, I've got that in here and here. I think I run this one. Okay, trainer evaluate. Oh, right, it's happening, right? So as you can see, wow, we are mastering that subset, right? It's like 90-something%. This is good. All right, so who knows how to reach to 100%? Like in theory, at least, with some. Okay, here's why I asked that question. I've got a very smart friend at my university. Like, I really liked optimization. I was good at it. And he maximized one of the exams. Like, he got like perfect scores. Like, how did you do it? Like, right? I'm like, oh, it's easy. I applied simplex to all the tasks, right? All the exercise that we had to do. Like, God damn, right? And he maximized. He got, and like, the scores were normalized to his score in a sense. He didn't do everything exactly in the same way, but I was using different optimization techniques that I was told, and he just mastered one and applied to everything and maximized. So very smart guy, right? It shows different brains are working in a different way. And then he's like, okay, I'm starting machine learning and I'm playing with Kaggle, and I've got 1 on MNIST classifiers. Like, all right, how did you Like, what do you mean you've got one? I know that you cannot get one, right? By definition, right? It's just, oh, I've made a mistake. I use also test data to train my model. And then you beat it to death, you overfit, and then you've got one. It's very simple, right? Anyway, it's not a good practice, right? So what we are observing in here, training loss, validation loss, and just accuracy, those are good scores, right? Really, I think we are almost done. And then we just run that on test site and final just one score at the end of training. That's the way how you do it, right? You've got those 3 splits just to make sure that I was telling you about kind of that leaking, right? Of when you're changing the architecture and so on, you're kind of leaking your expertise from fine-tuning to from the validation sets to the training. That's why. Let's get another score just for the test set, which is separate. I don't know. I think that it's separate. It should be because, oh no. Okay, this, once again, this data set, it's once again old. It had only 2 splits, train and test. Normally, now we've got even more. So let me give you a heads up on, for example, like some challenges in machine learning, in computer vision, and so on. Now they've got 4 splits. Let's say there is this visual genome, or there are some VQA challenges where there is 1 split for training, 1 split for validation, 1 split for testing, and 1 split that is hidden just for the competition. You don't have access even to it, right? You submit your model, and then they're just providing you the inputs, not providing the outputs, right? And then you just submit your outputs. Depends, right? But it's more than, I think for VQA, there's this awesome GQA paper, like from Drew Barrymore and, oh my God, what's the name of this guy? Christopher Manning, right? From Stanford. And GQA had actually more splits, right? And it's, and it's progressing, right? But this is very cool data set. We've got a few minutes left. Actually, we've got plenty of time, right? Left. So you're training. I'm just, chit-chatting. Let me show you. This is very fascinating what they did, right? I was mentioning, okay, we are using accuracy. So GQA is a VQA data set, visual question data set. Maybe let me show you. It's an old one, right? From the, where's visualize? But they did a really cool job when it comes to looking at the biases in the data, looking at different distribution, right? They really polished, the text and clean vocabulary and the images, just to make sure that, scientists fully understand that data set. What was the problem with, let's say, VQA data sets, V1 and V2? There are no examples? There should be some examples. Their faces, this is great. Right, and they also did an awesome job when it comes to different metrics that they thought are important, right? Like consistency of the model outputs, or grounding, right? When they measure, like, for attention models only, so you can additionally measure whether the model, when it's providing the answer, is looking at the right pieces of the image and so on. It's yet another very interesting part of machine learning research, right? Is how to measure the progress. And as you know, with GPT-4, God damn it, you're using tests for humans, right? It's passing SAT, it's passing, I don't know, some medical tests. It's just, how is that even possible, right? It's just mind-blowing what's happening down there. A big part of that technical report is like, hey, we did this, we did that. Just only the scores, right? It's like, oh, how did you get there, right? Like, how did you get to that score? What did you do? We need more meat as researchers. But super impressive still. All right. Are you guys good?
Well, we spoke about the data and the architecture. When does compute come into play? OpenAI has spoken that when you increase compute, and some problems just get resolved automatically.
Oh, let me show you this. I think the paper is called On the Emerging Properties of Large Language Models, LLMs. Because I've got in my head, is this from that team? No. Why there's no? Sebastian Bubeck. That's not the paper. That's not the paper. Let me do this. because I've got a picture in my head where they're showing that almost like a tree. Okay, this should be sufficient. Please take a look at this. Oh, hi. All right, that's awesome. Stanford. So in here on the x-axis, they are just putting model scale, training, petaflops. It's just they want to simplify everything. But right down there, what we are seeing is like, okay, the size of the data set, the size of the model, kind of like, on that x-axis, trying to come up with one axis. And then how, depending on how much time you spent and how much data and how big was your model, that something that is getting just better, right? In those arithmetic tasks or multitask NLU or some words in the context, right? And they're showing that for different models, right? And it's training, right? So you train longer or more data, and then magically, model is starting to capture math. Like, how is that even possible? It's literally just, of course, there is some math in the data, right? But, it's something about reasoning that starts to emerge. Is this what you were asking?
Yes. So this is just about the training. Once you're running the model and getting it to respond with outputs, then you don't need that power.
Yeah, well, you evaluate, right? So those are the scores from evaluation. So really, if you're interested in this, okay, that's Spark. So Sebastian is talking a lot about this. He's like a rock star right now, I think. He gave really good plenary talk during the AAAI conference on AI that I just went in February. I would look for the talks on like emerging. Look at Sebastian Bubek, right? He'll give you more because, like I said, like life is not fair. They've got access to GPT-4 when nobody else had. Like, goddamn, Microsoft, just 10 billion and you can have it, I guess, right? Just 10 million bucks. But it's awesome, right? Because he's really like, he's, putting, researcher hat. It's like, okay, let me take my scalpel and, all right. So this checkpoint, what do they've got down there, right? It's awesome. I really like what he's doing. Props to Microsoft and that team in particular. Cool. Any other questions, fun facts? What would you like to hear? Or you're good, overwhelmed? Please.
I'm super not technical, so forgive me tons of ignorance in this question.
It's okay.
With regards to token storage, like what's the current constraint for the amount
of tokens?
Yeah, of tokens, and then what's the future look like there?
Well, like I told you, right? Okay. There are some solutions. You mentioned vector databases such as Pinecone, right? Yeah, that's a natural way of extending. Imagine that right now, each of those vectors. Postgres vector? Postgres just released a vector database? Damn! Alexis, have you heard? Yeah, PG, Postgres.
I've just been told this. So
yeah. By the way, Pinecone just got investment, 100 million like a few days ago, right? They've got next round of funding, which is super cool.
You can run locally. There's some that also have a cloud version that you can pay for, but you can run locally. I can't remember the name right now. Milvius.
Yeah, that's another one.
There's easier alternatives than running Postgres.
But Postgres vector.
Sure, but there's easier ways. Like if you just want a quick vector database to experiment with, you don't need to run Postgres.
Yeah, I use Pinecone right now, but it's expensive.
Yeah, it's behind API, of course. This is how you make money now.
Yeah.
Behind API, and here you go.
Same with OpenAI API.
Yeah. Yeah. Hi. Yeah. Well, so this is the reality that I think this is like a turning point, right? But like, of course, everyone, we understand why OpenAI kept that behind API, right? They didn't want to release that in the wild, and then everyone will be doing what they're doing with Llama model. Let's say like, all right, let's harvest, let's shave it, right? But also they are putting that behind those guardrails, right? Behind, I think that I fully understand, let's say, and fully support what they are doing this regarding, what the community thinks that, they are not that open anymore, right?
Well, yeah, I mean, the irony with the headlines you showed at the beginning of this was that Microsoft originally invested in OpenAI to democratize.
Oh, well, Elon Musk invested because he wanted to democratize. Okay, so here's the funny fact, Okay, OpenAI was formed at the end of 2015. So happens, I was at NIPS, back then it was NIPS, now it's New Rips conference, and I went to a Google party. Around 2 a.m., one of the guys from Google Brain, like, have you seen Ilya? Have you seen Ilya? Well, no, I don't know the guy in person, right? But all right, I was like, what is happening? Like, he wants to do something stupid tomorrow. The something stupid next day was that Terence Sejnowski from like big dinner, like 4,000 participants, like, I wanted to congratulate the founders of OpenAI. So I was on a party right the day before when they were like, okay, we are doing that, right? It's so funny, right? And the idea was that they will be open, right? And Terence Sejnowski from the Synod, Terence Sejnowski rings a bell to anyone? Like, okay, another prominent figure, right? Chair of New Rips, his papers with Hinton from back in the days, like 80s, 90s, like great figure. Anyway, he was saying, yeah, and it will be open, right? Open research, democratized, and so on. And from the beginning, they were driving along that mission, right? They were giving for free in reinforcement learning, right? Jim was the bomb, right? Like really, it drove, progress in reinforcement learning a lot. I'm not even showing a lot of really cool stuff that OpenAI did because I just focus on LLMs, right? But I've got much respect. And at that point, my comment is that I understand their motivation and why they start to be more hesitate more. And I fully understand also Microsoft position. Here's the deal. In order to train those models, you need a lot of resources. The original, like however millions they've got, like from Elon Musk and like from Y Combinator, of course, it wasn't sufficient, right? We were talking about lots of compute, and Microsoft was slowly pulling them, and moreover, they wanted to attract talent. And in Bay Area, how do you attract talent if your company is non-profit, right? It's hard, right? Because you're competing with Google, with NVIDIA, and all of them giving you equity in this or that form, in stocks and so on, right? So they're facing that problem. That's why they formed that capped for profit, right? And then so there are two organizations as far as I understand the structure. They know more. I'm who am I to say even something about their company structure? But I understand, right? They needed more capital and they needed to attract talent. That's why they formed this. Still, it's capped for profit. Everything that goes beyond goes to that non-profit organization, which is cool, right? And their mission is still intact, I think, right? They want to drive that in their way, and I think that with the research, the quality of the research that they're driving, they've got full right to do whatever. If they'll turn for full profit, I would say, well, you've got full right? As long as you're doing what you're doing. And Microsoft played that game very well. Like I'm saying, it's like showing a lollipop. Hey, you want more? Here you go, right? And it's one chance in a decade when you can beat Google. I'm like, if I'll be like CEO of Microsoft, like I would say, yeah, all right. What is 10 billion if I can just now laugh and say, hey, we've got better, AI in our core products, in Office. Our clip is better than your palm. How cool will that be, right? In your face, right? It's amazing what is happening. And I understand, right? I think it's a win-win situation, right? Imagine this technology will be available to everyone on the planet in a blink of an eye once they will decide to do it. And of course, do you know that OpenAI left the red button in there? If you listen to Sam Altman, like Lex Friedman was last interview with Lex Friedman. Yeah. He's saying down there that part of that deal, we're talking about 10 billions, right? And part of that is that at any moment we've got to try to press red button and turn it off. Like, damn, that's bold. I respect.
Yeah.
Right?
As long as that red button works when they need it.
Have you seen, by the way, there was a role like red button? Have you anyone saw that one of the? Yes, job posting, right? Red button. Well, I love that. It's just laugh. All right, cool. I think, guys, thank you. I think you're very good. Yes. Oh, right. Ah, yeah, right. Thank you, sir. Most important, part of very important lesson of this tutorial is let's do fast fact checking, right? What have we learned? Well, all right, once again, we didn't train and validate model using Kaggle. Oh, wait, actually, this is correct. I was right. Oh, we didn't train. We only did fine tuning. Ha, that's the tricky part, right? So it's plus minus and apply strategies to mitigate overfitting. We didn't do any of that. I was just, they were, let's say baked into that learning rate scheduler. But yeah, I didn't teach you much on this, especially not as part of this conversation that I had when I was preparing this tutorial. But still, very cool, huh? So, closing remarks. So, of course, ask ChatGPT to write me those closing remarks. But as you can think, let's read my closing remarks. So, I want to say thank you to all the participants, right? And I hope that you guys got more interested. Probably you were here because you were interested or curious. This was really like entry level beginning, right? Machine learning, kind of like a crash course. I just wanted to show you what's down there and get you more interested. And I hope that you will continue learning. I wanted to express my gratitude for Edge and Node for hosting this amazing venue. I love this place, really. I remember that I was in here when it was still like, locked and like it was just prepared, and I entered that. It was amazing. Like, wow, I still love this place. And I wanted to have something in here since then. So thanks, George, for enabling me, and thanks to Trisha for helping with that organization of all of it. Yeah, so this is what I think. And now let's see what ChatGPT thinks. Ladies and gentlemen, how cool is that, right? And of course, I like to this. Speculate on the future. How did he know that we'll be talking about this? There was nothing in the script, right? He just figured it out, and actually that's right? I scratched it, but with green, is actually, yeah, we did that. We are speculating, right? What is going to happen by definition, right? All of us are betting. We've got our biases and concerns and our thoughts. Yeah, it's part of the deal, I guess, right? Thoughts. Through our tutorials on image classification using CIFAR10 and AG, I hope you are able to ignite a spark of interest and give your hands-on insights into the potential of AI. Oh my God. I encourage you. ChatGPT is encouraging you. How cool. I encourage you to continue exploring and experimenting with these tools. Yes, prompt engineering, all of that, right? Like, go deeper, go shallower, like whatever, just play. It's coming. I don't think it's, it's next AI winter is coming, right? I was showing you that book for a reason. There were like few times in the past when the funding for AI research, for machine learning research and neural networks in particular, let's say, drained. That book was first of them. There are like 2 or 3 such periods. In the 80s was also like lower, but then few guys like Hinton and Jan LeCun and Joshua Bengio were still continuing and cooking something in their basements, and like, goddamn, here we are now, thanks to their perseverance. All right, so I wanted to express my deepest gratitude to Edge and Node for hosting. Yay! Lastly, check this out. I like to acknowledge the tireless efforts of Trisha and George. Without your unwavering commitment and hard work, lots of love, right? From me and from ChatGPT towards you guys. Thank you. All right. Thank you once again. Safe travels, and hope you see at the future events. And of course, I said thank you to ChatGPT, and he said also, well, thank you. It was cool. Right. So that's all. Fine. Once again, we are Semiotic Labs. We are awesome. We are hiring with some headcounts that we've got, but we are doing not only AI research. So if you're interested, let's get in touch. Get another QR code. And I'll be sharing that presentation. I'll export that to PDF. It's already on our GitHub, like let's say the tutorials you'd like to play at home. Yeah, I don't know. I hope that you guys enjoy that, and thank you for coming. All right, now I can eat my sandwich. Right.
Thank you.
Pleasure, man.
Okay.
So you're not technical?
No.
So what do you do?
Well, I'm running a crypto startup, so we're a payment rail.
Oh, so you don't have to be technical to run a crypto payment system. Cheers.
Well,